We are located in Emeryville, California. And this is actually the building in which we are located. You can see our labs highlighted here on the 3rd floor. Emeryville, California is home to many industrial biotech startups and mid-sized companies even. And we've been really fortunate to be a part of that ecosystem. This is a fisheye view picture of our fermentation suite. We start at 250 ml scale amber reactors and go up all the way to 300 liter scale. You can see pictures in the back there. We are supported by Department of Energy, EERE, through Bioenergy Technologies Office. We are primarily here to understand and solve scale-up challenges. So someone has a novel technology that was developed at milliliter scale, and they want to scale up to produce the first kilogram prototype. That's where we come in. We help them out through that process. Why do we exist? Those technologies that are developed at milliliter scale often do not perform in bioreactor with real-world feedstocks. The behavior is completely different. Culture experiences completely different conditions. So that's where we come in and we re-optimize the process. We also do quite a bit of downstream processing, and I'll go over that in a bit. We meet our collaborators where they are. Many of them start at the milliliter scale and come to us, but some of them have a decent sized process engineering team, in which case we would just directly jump to 300 liter scale with them. Most recently, we've invested in a pressurizable fermentation capacity, so to be able to simulate conditions in really large scale where the lower layers of the culture would experience substantial high pressure. And we've done a study with Checkerspot, which has been made public to show that their technology was able to, their culture was able to survive those high pressures. And we also do a bunch of chemistry upstream and downstream, start at the milliliter scale, go up to 200 liter scale with H.E.L alloy reactors, which means we can use high and low acid concentrations. We can run vacuum, high pressures, a variety of different types of chemistry. We have a dozen or so downstream unit operations. Even then, we don't seem to have enough, in which case we rent equipment from our vendors. You see the italicized equipment here. They rent equipment to us. We install it, commission it, use the capability for our collaborators, and then unpack and send back to our vendors. We have core capabilities that we need at the ABPDU, but sometimes we do need these additional capabilities, in which case we would just rely on our parent organization, Lawrence Berkeley National Lab. If you're not familiar with the Lawrence Berkeley Lab and its user facilities, I would encourage you to look them up. You can engage with them directly as well, but we're happy to work with them to perhaps maybe understand a certain protein or learn its structure, etc. Molecular Foundry and Advanced Light Source are world-renowned for this type of work. If we were working together, today would be our first initial contact where you are meeting us. It usually takes about 12 weeks to start a project with us, especially only if you are a US company. If it's a foreign company or if a foreign national is involved in the equity of the company or at the C-suite level, perhaps in the management of the company, then it takes a little bit longer because we have to go through the foreign review process. But if you were a US company, this is our initial contact. We would walk you through, after doing the NDAs and reps and certs, we would do a project scoping. Project scoping would be at a very high resolution, about 4 hours per subtask. And that way we can be sure that the company is very aware of what are all the tasks that are being executed on the project. And then we go through the formal budgeting, contracting, and EHS review, substantial EHS review. It turns out that our EHS review actually helps companies long after they've left ABPDU as well. It helps them safely scale up their processes elsewhere too. This is an exceptional case in which we initiated a project within 6 weeks. We can't promise this every time, but if there is an urgency, like there was in the case of H.E.L, where Michelle Zhu wanted to demo some indigo dye coming out of a fermentation process in their demo day at Indie Bio Accelerator program, we were able to initiate the project, scale it up, and do downstream within 14 weeks. We were able to provide the indigo dye that went on an industrial machine. And you can see here Michelle is showing that to the audience. So this is how we helped 85 companies, more than 85 companies, small and large. We worked with the Totals of the world, the Shells of the world as well. So we're open to working with anyone. We worked with a bunch of academic institutes as well. So these are our academic collaborators. We support industry in writing support letters, co-authoring proposals to SBIR grants. Feel free to reach out if you're interested in that. We've helped put 17 products in the market. That's really our goal, is to accelerate the process of taking an innovation from a lab to putting products in the market. We conduct industry listening days. We've conducted 2 of these. These are not as frequent as the expos because we get a lot of feedback from our collaborators. It takes a little bit of time for us to catch up on it and provide the results, provide the feedback, use the contribution on the feedback. One example is gas fermentation capability. So the pressurizable reactors that I've mentioned, we've also been able to use these reactors with a manifold for many gases to conduct gas fermentation at half-liter scale. And now we're working with half a dozen or so companies that did tell us in 2019 to invest in this kind of capacity. We are now in the process of commissioning 20 liters of this gas fermentation capability. So we'll come to this topic today. ABPDU Virtual Expos, we conducted one last year, which was very successful. If you missed it, you can go to our ABPDU channel on YouTube. You go to YouTube, search ABPDU, and you'll find all the sessions at the Expo. Last year's theme was scale-up facilities, mostly scale-up and manufacturing facilities. This year's theme for us is software, equipment, and expertise. So if you missed yesterday, we had a whole day of software, data, and AI talks, some wonderful talks, and we recorded these. Unfortunately, we cannot put them online immediately. They have to go through a review process, so it'll be a couple of months if you've missed it, but you can find them on our YouTube channel in the new year. Today, we are going to start off with equipment, mostly from our collaborators from Europe, because we want to give them a chance to present at a decent hour. Then we go into expertise, again start with our European collaborators and move into the American contributors, and then eventually we'll go into equipment. So quick instructions. Please stay muted at all time unless asked by a moderator, whether you're a speaker or not. Please stay muted until you're asked to. This is not a webinar format. This is a direct meeting format, so we request you to stay muted. If you have any technical issues, you have any questions or concerns that you need to share, please write to us at abpdu@lbl.gov. 6 of us are monitoring this email ID so we can respond to you immediately. If you have any questions, please write those, or comments, please write those in the chat section. The speakers are expecting that you will write the questions in throughout the talk, so you don't have to wait until the end of the talk. So I'll stop there and very quickly thank the ABPDU team that does the fantastic work of the scale-up and develop the scale-up expertise that we have. And very quickly, any questions, comments, or concerns? Okay, so I'll now hand over to Eric Sundstrom, who's our moderator for this session. Thank you, Eric.
Thank you, Deepti, and let's get right into it. So our first speaker this morning is Martin Currie. Martin is going to be talking to us about open source protein production platforms. Martin, I'll hand it off to you. You can go ahead and share your screen.
Thank you very much, Deepti and Eric. Can you hear me okay?
Yes.
That's a relief. Excellent. Yeah, so AMYBO exists to provide sustainable protein for all. We're all here about scale up, but I thought I would just take you through our motivation for scale up, I guess. So we've got a 50% chance of exceeding 1.5 degrees of global warming in just 7 years' time. So that's the continuous 1.5 rather than the 1.5 that's already forecast for this year. As crop failures become more common, things like solar-powered bioreactors could become a life support system. And don't get me wrong, I don't mean this as a downer. I'm hugely excited by the fact that hydrogen oxidizing bacteria can get us out of pretty much any food crisis that I can think of. Can you, in fact, let's see if the chat's working because I haven't seen anything so far in there. Can you think of any other foods that we can grow in a nuclear winter? I'm just wondering if the chat thing is my fault and I'm in the wrong thing, because I'm so far only seeing messages from Deepti. I'm seeing spinach from Deepti. Interesting. And mushrooms from Eric. Good. Okay, so I'm seeing more than just Deepti. That's brilliant. Not that you're not enough Deepti, but anyway. Yeah, even mushrooms need organics from dead photosynthetic plants. Hydrogen oxidizing bacteria are the only food that I can find that we can make with just the wind power that we could harness in darkness. And if AMYBO succeeds, we'll be able to easily grow them in our own homes during lockdown. They're also the best food for space travel, as they require the smallest grow spaces and only need solar energy, the otherwise toxic carbon dioxide we breathe out, and a little recycled wastewater. Meanwhile, back on Earth, food's not just a symptom of climate change, it's responsible for between 26 and 34% of global greenhouse gas emissions. By providing an attractive alternative to meat at a lower price point, we could reduce global greenhouse gas emissions by at least 8%. Livestock also takes over a third of the planet's habitable land, with massive impacts on biodiversity, and each year 13 billion hectares of forest area are lost due to land conversion for agricultural uses. An affordable, attractive, low-footprint protein could also reverse this trend. With hydrogen oxidizing bacteria, we're working to let anyone anywhere ferment tasty, nutritious protein from not much more than sunlight or wind power and carbon dioxide. Once it's fermented, all you need to do is pasteurize the solution and then spray dry it as if you were making milk powder. And you have a lovely near 70% protein, nutritionally complete flour, which some excellent startups have used to make pasta, ice cream, sauces, chocolate, noodles, meatballs, pancakes, and much more. So where AMYBO differs from other startups is that we're a non-profit community. We're building on existing open source solutions like this small but certainly, well, it's 20 mil scale bioreactor called PyReactor. And all the solutions that we're making in terms of hardware and software are open source. Our first big step was producing the electropyreactor. The second is then going to be lending them out free of charge to volunteers to isolate the best strain of hydrogen oxidizing bacteria. So when your bioreactor arrives, you simply head out to a local beauty spot and take a water sample. The way we're going to find better tasting, superior strains is by looking for them in more places. So I sampled mine from the source of the River Cole on New Year's Day, but I thoroughly recommend that you pick a warmer time of year, as some of our Harvey Mudd clinic recently did. Then you pop your sample in your free bioreactor with some trace minerals that will send you, and the bioreactor will stir it. It'll measure and maintain its temperature and measure its optical density. You can add various other optional sensors, like there's a $20, I think £20 at least, maybe a bit more than that in dollars, spectrometer, if you'd like to measure its color. You plug in the electrodes and they'll produce hydrogen and oxygen for any hydrogen oxidizing bacteria in your sample. By adding a SodaStream cylinder, the system can sparge carbon dioxide as the carbon source and to purge its excess oxygen. Set it to auto and it'll happily enrich hydrogen oxidizing bacteria with very little input required from yourself. Although being open source, you're welcome to tinker as much as you like. So we've made this so affordable that we're planning a pilot trial, hopefully in the new year, where we give volunteers a free bioreactor. Now let's see if I can get mine up on screen. Yeah, here it is. Sorry, I'll zoom in. So this is it. You got a 20 ml vial, and oxygen is formed on this electrode, hydrogen on this electrode, and then we take trace minerals from this centrifuge tube, which come in through this peristaltic pump here and go in there. And then the second main thing is carbon dioxide taken from a standard SodaStream cylinder, then goes through just a regular regulator, solenoid valve, which is all controlled automatically by the Raspberry Pi, which it's refusing to focus on, but anyway. And then basically the product comes out in this centrifuge tube here. So Yeah, all we ask in return for the free rental is that you open source your experimental data through our data sharing platform. We'll be able to identify the most productive of thousands of strains from around the world by monitoring the optical density growth. And NCIMB, that's like a patent depository in the UK in Aberdeen, not too far from us. They then provide whole genome sequences of your most promising strains and conduct European FSA toxicity screening on them. We'll conduct a thorough risk assessment together, then you might want to taste yours. I've been dreaming of making pancakes with my own hydrogen oxidizing bacteria ever since I read George Monbiot's Regenesis. Beyond the 20 mil, I thought since this is scale up, I should just give you a little advanced preview of some work that we're doing here. So this is a TRL4 example that we scaled up to 1 liter. It's just making kombucha, but we've also designed sub $1,000, hopefully, 1,000-liter PioFlow. So basically, what it does is it takes the standard bioreactor that we're using and uses it as a flow-through cell for any larger vessel. So as long as you've got something approximating an ideal continuously stirred tank reactor or a reasonable plug flow system, it should be able to control all of that. And we're also working on an additional system that will give us a larger flow through rate in case you have sort of more dense optical density stuff. So yeah, I'll head into questions now, I think. So you can head to AMYBO and get involved, really, find out more. You can email me at martin@amybo.org. And yeah, together we can provide sustainable protein for all. So in terms of questions, how do you assure quality across contributors? That is an absolutely brilliant question. So I first met Deepti actually when we were working on some potential AI solutions. There's a couple of sides to it. There's the physical side. We're going to be doing lots of stuff to ensure that everyone has as similar a physical configuration as possible, because obviously that's going to make a massive difference. And a sensible route around it also is to have them set up in pairs so that we are basically looking at the difference that you have between your two systems rather than the sort of absolute difference between you and somebody on the other side of the world. We're also working on an interactive video tutorial system that will help get the human factors a bit more consistent. And then, yeah, the AI system will basically be looking at as much as it can, trying to determine what's a genuine difference and yeah, what's just because somebody's got their electrodes slightly differently configured to others. Thanks, James. Any other questions?
This
Here's
is really
my email
cool,
address
Martin,
as well,
and
if you wish.
sign us up for our free bioreactor. So
Brilliant,
question
thanks.
that comes up when we do this type of work all the time is around the safety of mixing hydrogen and oxygen in these types of fermentations, and how to approach making sure that nothing can go wrong in that kind of a setup. So I'm curious at the very low price point you guys are shooting for, how do you manage that?
Crazy, yeah. Yeah, exactly. Is basically we're not using hydrogen gas. I mean, obviously we're using hydrogen gas, but we're not pumping in hydrogen gas, which is what most people do when they're making hydrogen oxidizing bacteria. Instead, it's forming on the electrodes. And what we're seeing is that you only see a little bit of hydrogen gas in the headspace fairly briefly at the start of a reaction. And then once that's flushed through and the bugs are growing, they're basically consuming the hydrogen as quickly as it can be produced. So it's, yeah, basically hydrogen is the rate limiting nutrient. Off topic. How did I do my presentation? So yeah, I had a prior startup called Andai. We were doing online conferencing, and this was one of the tools that we developed. It's Yeah, unfortunately, it's nowhere near as cheap as our bioreactors, so it's not quite as scalable. Cool. Any other questions, or have I don't know, have I outdone my time already, Eric?
Yeah, well, I guess if there's no further questions, if anything comes to mind, please feel free to drop it in the chat, and hopefully Martin can stick around and answer anything that comes up. And we'll go ahead and hand it off to our next presenter, Matthew Scheier. Matthew Scheier from OGI Bio, and he's going to tell us about a new system for reproducible and reliable growth automation for microorganisms.
So my name is Matthew. I'm from OGI Bio, and I'm telling you about the OGI system, which you can see here, which is starting shipping at the end of the week. So exciting news for us. And we started off looking at shake flasks and deciding it was the touch time was a bit too high, the data yield we were getting. So we came up with this OGI system. And what you can get is a modular system, mainly because we started out as academics and decided, wouldn't it be nice if you could just buy everything in parts? So what you get here is 4 independent bioreactors with working volumes between 15 and 20 mil, with independent heating and independent stir speed and Wi-Fi and software capabilities. And then you build up from there. So let's say you get a bit more grant money in and you want to install a dissolved oxygen with 1 screw, and you can start collecting your data. Or maybe you're looking at a protein or a fluorophore of interest, and fluorescence becomes important. Well, and again, 1 screw install, and away you go. And then you maybe decide pH monitoring is important for your experiment. Maybe you're producing some kind of metabolite that'll change your pH. And then you pair it with our liquid control, and that allows you to control pH, start doing fed batch, continuous experiments, or maybe set up a chemostat or a turbidostat. And then maybe you decide, well, actually, my interest is I want to have the highest cell density I can have, or maybe I don't want oxygen being a limiting factor anymore. Well, we have a sparging module for that. Then you can control all of this through our software. So our first goal with our OGI was make sure we can match growth rates of shake flasks and take the box there. Your next question might be, well, will my bug grow in it? So far, so good. What you're looking at here is some media optimization for Saccharomyces in biological replicates. And then you might say, well, I've got a very odd bug. So Archaea. So these were grown directly from colonies at high salt and high temperature. We've actually taken this up to 76 degrees. A little bit more about our dissolved oxygen module. Provides real-time dissolved oxygen concentration. Obviously, you can go from anaerobic to fully aerobic. You can achieve oxygen rates similar to shake flasks, and we can vary. Obviously, you can vary each bioreactor individually with setting your stir speed. Here you can see various dissolved oxygen and optical densities. So our standard input is 4,000 RPM, and what happens there is about 14% dissolved oxygen. And you see this directly compared to shake flask side. Now you can take fully aerobic system and let it deplete itself of oxygen, or you can just have an anaerobic system from the start. And these can either be sparged and depleted of oxygen, or just put in, and they're small enough to be put in anaerobic hoods as well. A little bit more detail about our liquid control. We have 1 input pump and 1 output pump. And you can also, you have done 3 inputs to 1 output for a customer previously, so that's something else to do. And yeah, you can pause at any point to extract that. This is all based around our glass vials and bungs you can see here. And obviously you can set a different turbidostat or a different flow rate for each bioreactor. We've done sort of bang control, and we've also done PID control. So depending on the level of precision, we can find that for you. And we also have no problem at lower optical density. So a little case study, we had some people looking at Streptococcus pneumoniae, and they wanted to replicate this previously published figure by adding their bug to a chemostat. And the oscillations you're seeing here are due to Streptococcus pneumoniae's virulence factor Lit-A causing autolysis once the stationary phase is reached. Now to do this, you have to set up your chemostat. You have to be there for every hour of the day to sample, in triplicate, dilute, plate, wait 24 hours, and then start counting. What we did in 48 hours is set up calibration, inoculated, went home, watched Netflix, spent some time with the kids, came back, and captured these oscillations, which I'm sure we can all appreciate. Done something similar as well with mixed culture dynamics. What you can see is in blue and gray is the strains by themselves, and in orange and yellow once mixed communities. And then obviously just monitor the saturation. And what you can see, what you can't see, but was monitored by fluorescence is strains becoming dominant. And then we also managed to confirm this by flow cytometry. So it's all about letting you go home, enjoy your day, and not have to be there to maintain your shape file. So fluorescence module, as a bit we spoke about, we standard have red, green, and blue. We've used it for optogenetics, and we have a range of detection so that we can actually customize your LED for your PET photophore. And again, we can install these with one screw. And it's just brief capturing fluorescence signals. And then just want to talk to you a little bit about our new pH modules. So again, independent monitoring or control each bioreactor. Full range of pH, and as I mentioned before, we can do acid, base, and feed inputs required. Sparging module, again, if you want to limit it, oxygen as the limiting factor. You can set independent sparging rates. You can also get the real-time feedback loop preventing depletion of oxygen, and it's all compatible with commercial filters. So again, yeah, monitoring and control pH levels, all controllable through our software. And yeah, if there's any questions, I'm happy to take them, and feel free to contact us.
Thanks, Matthew. Got a question from Martin. Which pH probes do you use?
So these are standard pH from, I can get that information to you, perhaps if you DM me with email, but yeah, they are bought in, so yes.
And with the pH module, would you be able to control pH and say run and fed batch at the same time with multiple multiple feeds and feed controls?
So as standard, we have one input, one output. So depending on, so essentially we could do, if you were running a buffered system, we could try and control pH whilst having some kind of buffered media. But if you're just looking for just pH control, then no. But we have done acid, base, and feed. So three inputs, one output. But that does mean sacrificing a bioreactor for that. So you could run 2 bioreactors with 3 inputs and 1 output and sacrifice 2 bioreactors if that's something you're interested in. But generally we have 1 in, 1 out.
Right. And so then the feed control is just customizable based on feedback from any of the sensors and probes.
Yes.
And so I see it's set up for 4 cultures right now. Are you guys looking at pushing to even higher throughput at some point?
So if you purchase multiple systems, the software allows you to link them together. So if you were interested in having multiple systems, they can all be run through one bit of software.
And then another question I had, so you mentioned it's good for semi-anaerobic. Sorry, they're good for semi-anaerobic and anaerobic. I see. Okay, so you can run anaerobes.
Yeah, so I've done that quite a few times. Our system is probably smaller than the footprint of the majority of people's laptops sitting in front of them. So it's quite easy to fit the system in an anaerobic chamber, but we've also had people sort of sparge the glass vials and go.
And so what's next for you guys after the pH control module? I guess what can we look forward to seeing further down the pipeline?
So sparging is pretty exciting as well. That means higher optical densities being able to be reached, and then removing oxygen as a limiting factor. And then I think the next sort of big thing will be setting up splitters so you can extract from your bioreactor without having to pause the system. And then from there, we've got some sort of exciting microscopy work.
To be able to do real-time microscopy.
That's the plan.
Great. Oh, powerful system. Any other questions for Matthew? No, let's we can just one more question.
I'm not, but I'll grab your email and I'd love to discuss a little bit more.
The question is, I read these out so that we can have them on the YouTube. Are you in touch with the team at Oberflexure?
So yeah, not at the moment, but I'll grab your email and I'd love to discuss that further with you.
All right. Yeah, thanks, Matthew.
Thank you.
So our next talk will continue in the same theme. So we have Manfred Satzer joining from P4B to discuss a downscale solution for biomanufacturing. So, Manfred, I'll head it off to you.
So thanks for the introduction and the invite. I'm one of the two founders from P4B, and we thought about a completely different solution to tackle the scale-up issues. I don't need to teach the ABPDU about the risk and the problems when scaling up, but essentially it's complex scaling transitions. The processes behave different in large volumes because they simply mix worse than the small ones. And it's very expensive to do experiments in large scale, so you're not able to adapt your process that much or even do cell line development in large scale. So we thought about a completely different approach. We're making the small scale mix worse. So essentially, we create a wall structure in small scale lab scale vessels to change the mixing behavior to adapt them to the large scale. So we can create mixing times of up to 150, 300 seconds without any problem, and also adapt the mixing curve so that your process runs similar to the large scale. So you can do process exploration in the small scale with your lab scale system that you're already used to, and then scale up more easily. we're not trying to replace the pilot project, the pilot reactors completely, but to make it easier to get to these volumes. As Deepti mentioned, 50 milliliter is a good starting point. I mean, this is one of our AMBER 250 inserts to change the mixing time there. So essentially, the customer comes to us with the target reactor system. We create a digital twin from that. We don't need to model the cell itself. We need the fluid dynamics. So it's more about mixing, starvation residence time, for example. Then run it through our evolutionary eye to create a wall structure for a vessel or an insert for a vessel to replicate this mixing behavior in small scale. Then we 3D print it and then send it to the customer. So you can do your process exploration much earlier than was previously possible. So you can do it, start at 50 milliliter if you want to, and you can explore completely new possibilities that you didn't have before. I'm sorry, that was, yeah. I mean, it's applicable in this case for food proteins and biofuels where the fermenters are really huge. And the large issue is the glucose and nutrient gradients that form, or oxygen, CO2 too. And the good thing is that you can redevelop your processes there and adapt it to get a better yield or quality. But it's also applicable for biopharma chemical processes as well. So we can adapt it to stir tanks essentially. So one big issue, as mentioned before, is glucose and nutrient gradients that happen. So there's a lot of nutrients at the top and a gradient to the bottom. So the cells explore starvation there, which is for high cell density even worse because you've got a high growth rate, high nutrient consumption, and these gradients, similar, they form. They don't form in the small scale because they're so well mixed. And you see the effects only when you scale up to a larger volume. And the issue is even worse because it's been shown that even short-term starvations that were repetitive caused cell metabolism changes that last much longer than the residence in the starvation times. So what we did is, this is for an example of one of the structures that we derived. If you look at the diagram at the left, you see the conventional 1.6 liter vessel that's used. It has a mixing time of about 9 seconds or 10 seconds. And the green one was our target 54 cubic meter, which has a mixing time of nearly 60 seconds. And when running through the generations of wall structures, we were able to achieve an insert that has or nearly matches the mixing curve of the large one. Because it can have a mixing time the same and only one small unmixed pocket, but that doesn't replicate the process conditions. If you can achieve the same mixing curve, that's much nearer to the large scale mixing. So what you can do with that is we offer a standard reactor range where you can just by mixing times 10, 20, 50, 100 seconds to explore your process and expand your design space. This wasn't previously possible before, but also with different nutrient starvation residence times, or we can build custom downscale models for your project, for your production reactor that you already have. To do specific testing or specific production challenges. That's just one use case that or a pilot project that we did, is scaling down a reactor to a 200 milliliter system, which was quite challenging because there's so much sensors in there. There's not much space left to create any structure. But it worked quite well. So that's one of the evolutionary mixing time adaptations, reaching from standard 20 seconds, 25 seconds, up to 300 seconds. And these are all variations of different mixing curves that we were able to achieve. So it's not just using an AI and plop, the wall structure that's needed comes out. It takes some calculation time, and we need a CFD. simulation for that as well, but it worked really well. And these are the products that they look like. It's inserts if possible, or otherwise we just exchange the whole vessel. So you just replace your, I've got one larger here. You replace the whole vessel, put in the sensors, screw on the head plate, sterilize it altogether or autoclave it, and then use it in your process. I see Martin is quite skeptical. Yeah, that's not sure why it doesn't start. That's a video of a tracer that's put in there. You can see at the left the one without any ball structures, and then there's 3 different ball structures used for 69 and 120 seconds mixing time. So it's just for visualization to give you a feel for that. Yeah, we've already proven that it works. I mean, we've got a number of pilot projects coming up in January to get us a better data foundation. Our bonus point is that we can create custom solutions since they're 3D printed, and we don't need a lot of pieces to be sold, and we can tailor them to your specific need. And the bonus for you is that you can have an accelerated development already in the lab, and it's very cost effective. If you even save one large run, yeah, that saves a lot of time and effort there. So, yeah, if you're ready to revolutionize your process development, please get in touch with us. Yeah, there was a question from. Okay, there's.
Yeah. So the question here is wondering, would it be feasible to adapt your bioreactors to simulate hydrothermal decomposition processes in addition to enzyme-based applications? And what would be the challenges or considerations?
I'm afraid I'll have, perhaps it's possible to get a private or to DM me, because I'm afraid my brother is our biotech process expert and he's not available today. So I'll have to defer that question for later, I'm afraid.
One question I had, I'm curious about how you handle viscosity, especially variable viscosity across a process runtime, and how that might impact mixing times and design of your inserts.
That surely is an issue. Yeah, we can simulate different viscosities, and we would use one at the start of the process and middle and at the end, and then try to determine a rating of our wall structures from these combined from these combined simulations. So we don't have a rating specific to one property like the mixing time. We can combine a number of mixing times or mixing curves or even oxygen distribution to achieve an overall result that is the best fitting one.
Then I know, in this space, it's at least somewhat common to do downscale modeling by essentially temporally varying these parameters in a well-mixed bioreactor system. So varying, say, the dissolved oxygen along some either random or sinusoidal curve. I'm curious how this would sort of, could you compare and contrast this approach against the approach of varying things in a uniform mixed system, but temporally?
The two are not exclusive. I mean, what we can really do well is decouple the stirrer speed from all the other parameters, because we can have a bad mixing with large stirrer speed, or even worse oxygenation with a large stirrer speed. So it may not be excluding. What we replicate a bit better is if you've got a large tank, then there's not a good mixed region and one bad mixed region, or the cells there are gradients and they move through these. And even if you've got the temporal cut off of the oxygenation and then get it on again. Yeah, I'm a bit stuck there, I'm afraid. We don't have direct comparison right now from any process that we ran, if you are pointing at that.
Yeah, actually, that was going to be my next question. So I would think, for folks who are on the call right now, are you looking for example processes or application notes or folks you could collaborate with who could provide that small to large scale accessible data?
Ideally, yes. I mean, what would be good is if someone's got the large scale data and has problems there, if we can replicate these problems in small scale, that would be our perfect pilot project or proof of concept. So we're quite early. We were only founded at the end of 23. And so we're currently looking for challenges that customers have to replicate them in small scale. So yes.
Right. Yeah, it's a very interesting approach and certainly not something I've seen before anywhere else.
There's a university in Germany that's got a similar approach. They're building bioreactors with a plate with holes in the middle to have two compartments, one mixed, one well mixed, and one badly mixed. And they got quite good results, and ours is more or less further development going from there. So the idea to have a badly mixed vessel is not that new. Yeah, but it's a bit of a further development.
Right. Well, yeah, thanks, Manfred. And yeah, please drop any follow-on questions to Manfred into the chat. And we can go ahead and hand off to our next speaker, who's Eric van der Meer. Eric is from Delft Advanced Biorenewables. And he's going to tell us about unique technology that they're developing for continuous extractive fermentation.
So thank you very much, Eric and team, and thank you for listening in. Switching to large-scale biomanufacturing, slightly different perspective, I believe, from what we've heard today. Starting at ultra high level, if we want to ever reach net zero, there's only really 3 sources of carbon that we need to use for everything that we need on the fuel side and on the chemicals and materials side. It either needs to come from CO2, biomass, or recycling of carbon that was manufactured before. And fermentation then is a subset of both using the CO2 and the biomass as inputs for renewable carbon. If you look far ahead, these numbers come from the Renewable Carbon Initiative, then energy carbon consumption, embedded carbon will have to drop by 50% in 25 years, transport by 65%, but chemicals and materials need to double. And of that doubling, a very large amount needs to come from bio. These are obviously projections, and there's other projections as well. But basically, there is a very substantial need for bio-based, both energy, but also transportation still, mainly in aviation, and also to a large extent in chemicals. Now, so what is the situation with the exception of things like ethanol and maybe lactic acid? Largely, biomanufacturing is confined to low volume, high value. You can argue about where the break-even point exactly is. For some products, $100 per kilo. For some products, a bit lower and a bit higher. But there's little evidence of plants producing biomaterials at more than a kiloton, as I said, with some exceptions. And the reason is quite simple. We deal with water. The water is an unwanted medium in manufacturing. We need to get rid of the water, need to purify the product. obviously we need the water, but the water is, and the batch process is one of the reasons why biomanufacturing fermentation is fundamentally more expensive than fossil-based manufacturing. We have taken learnings from the chemicals industry. We originate from more a chemical engineering mindset than from a biology mindset. And we've looked at how chemical synthesis takes place, how this has evolved, where both the synthesis and the product separation has been optimized, has been combined. Often there is a catalyst, often there is a reactant, a solvent, where the optimum of all of this heat, mass, water integration leads to the lowest cost of product in an almost always continuous and intensified process. And we've emulated this thinking into a bioreactor concept, which is the fast bioreactor concept, fermentation accelerated by separation technology. So we have a reactor where a liquid-liquid separation takes place, where the synthesis section is well mixed, turbulent, where there is an optimum contact as one needs in a fermentation between the carbon source, the oxygen, the microbe. And if you were to add it an extractant, in the top of the reactor, we separate the two liquids, the water from the oil. We take the oil with the product, separate out the product, recycle the oil, and have a continuous extraction process, if you wish, superimposed onto a fermentation process. And we now have an intensified fermentation process with in situ product removal as the key determinant of this system. And what does it look like? Going into a little bit more detail, this is a sketch of a fermenter, well mixed, well stirred, with a separation zone on top. The separation zone is always approximately 2 meters because you need a certain amount of height. The aerated broth organic mixture rises to the top because it is lighter because of the gas holdup. At the top section, through a riser, the air and CO2 escapes. The residual liquid is now heavier, therefore flows back in a laminar flow regime where there is demixing of water and oil. The de-aerated, de-oiled water broth, including microbes, flows back into the reactor, creating additional mixing power. And the top layer is skimmed off with the product in it and with a certain amount of water, because the alternative to skimming off the water over the top is some form of aqueous bleed that one needs. And what you now have is a system with a very low organic phase holdup in the fermentation zone, therefore a very low propensity to emulsification. We control the residence time, and we are able, and this is really significant, to set the set point of the fermentation by adding and removing more or less solvent. One can set the aqueous concentration of the product that is being removed. And in the case the product itself is oily, for instance, a long chain fatty alcohol or fatty acid, one could remove that product continuously from the fermenter, preventing that product from clogging up, from emulsifying the fermenter, controlling the concentration of that product in the fermenter to a very low percentage. So we bring a fermentation into steady state as much as possible for as long as possible. It is technically not continuous. It is technically not as continuous as a chemostat or a wastewater treatment reactor, but it is prolonged fed batch, if you wish. You continuously add a carbon source. You bring the organism into steady state by continuously removing the product. And as long as the organism holds on, as long as the decline of performance of the organism is acceptable, you continue the fermentation. And as a consequence, a substantial amount of additional product is produced from the same steel, from the same capex investment. This is an example of what this means. This is a 2-phenyl ethanol, so an aromatic compound that we have developed ourselves. strain obtained from the University of Delft, where we have simply through process development of getting our system to work, have increased the virtual titer, the amount of product produced, from 3 grams per kilo to 91 grams per kilo. The toxicity limit of this product is 5 grams per kilo. So you see an enormous uptick, an enormous performance improvement over the years by simply getting this process to work. And this is what it would look like if you look over time. We have run this fermentation for 10 days. You see that both yield and oxygen uptake rate remain pretty stable at a very high level. A slow decline as gradually cells die or remove or get removed with the water phase. But you see a prolonged fermentation of 10 days in a very with a very toxic product. And this proves the concept of ISPR. This proves the technology works on a very difficult product, and it works because it is an agnostic technology. It works on a very large amount of product. This is then the consequence of what this would mean if you were to build a full-scale plant, 7.8 kiloton per year, 2 times 300 meter cube fermenter, so a significant plant, of course. You would get a cost price of in the 4 or 5 euro or dollar per kilo range, and the current product that ends up in your detergent and in your fabric softener would cost around 4 to 6, and that would be based on coal out of Chinese chemical manufacturing. So we are able to now portray a cost-competitive compound based on sugar, competitive with a product derived from coal. These are some other examples. We are not always able to be cheaper than fossil. Of course, if that was the case, we would have solved all problems related to net zero. There is still usually a penalty. There's usually a green premium to be absorbed. Butanol, we get close to fossil. We get substantially lower than butanol produced until today, but we're still at $2.5 per kilo, where the fossil compound would cost maybe 1.5, 1.3. Farnesene, produced at relatively large scale in Brazil, a diesel component as well as a chemical feedstock, we can hive off a good 25%. And it's important to maybe mention here that we are now working on a C12 fatty alcohol. As we speak, we're doing a demo run in our demo facility. And that product could both serve as a palm oil replacement, but also as a precursor for sustainable aviation fuel. So we're working on a very large amount of application areas. And as a result, of course, this is again a schematic representation, but by bringing down the cost of manufacturing, we lower the break-even point to fossil, and we're now seeing the opportunity for 100 kiloton and more plants to be competitive with fossil. This is, in summary, what we do. The FAST technology offers continuous extraction with continuous product removal, intensified process with concentrated streams, therefore simplified and more cost-effective DSP, superior steady-state operation, and with depending on the product, fantastic metrics, up to 10 plus times more productivity. The example of 2PE that I showed is a 30 times improved productivity. 50 to 80% energy and water efficiency. All our unit metrics are substantially better. The only one that does not improve much is the yield. We still need more sugar to produce more product, but the ancillaries like energy and water and capex are substantially improved on a per kilo basis. And we now reach in the $2 per kilo range for oily products and in the $5 per kilo range for certain chemicals. And as we develop our technology and as we work with strain owners to develop the strains to match the specific properties of this technology, focusing on longevity, for instance, of the strain, resistance to genetic drift rather than on tolerance to inhibition, we believe we can get to substantially lower cost levels as well. I already mentioned that we have a demo plant. You see that on the right, beautiful bearded operator. To give you a sense of scale, it's approximately 4 meters high, 2 meters fermentation section, 2 meters separation section. The separation zone is always 2 meters because we need the height, we need the density difference, we need the settling surface to be able to separate water and oil. The fermenter would obviously be very tall if you were to build a full-scale fermenter. This one is operating now for 2 years in BioWaste Europe pilot plant in Ghent, doing very well on a range of products and for a range of use cases. And on the left, you see a number of the products that where the technology works very well for. Very hard to quantify. As I said, it's an agnostic technology, but probably half the chemicals that are potentially produced by fermentation, we would have a substantial or a very substantial positive benefit on. And that is really where I would end. Maybe since I still have a minute, maybe to add that we have developed 2 lab tools for our technology. A very simple insert that you can stick into your bioreactor so that you can continuously remove an oil fraction from your fermenter. So you can, at a proof of concept level, work on continuous product removal, continuous oil phase removal. And we also have developed the FAST Mini, which is a proper scaled down 3-liter version of the FAST technology, where you have continuous product removal, where you can do proper process development and process optimization, controlling quite precisely the product concentration in the fermentation compartment and hiving off the oil product mixture from the top. That device is currently being prototyped by us and by one of our clients. We have 4 units in operation, and depending on the learnings from the prototype phase, we will launch them in Q1 with potentially some small modifications. Glass device can be used, can be fitted to your existing controllers and pumps and what have you. So you simply need to purchase the glass device, and then you can have it your way. And it's important as part of our strategy that we bring the tools to work with continuous extraction to our clients, to our future clients, so that they can work on the opportunities without having to deal with an R&D agreement with IP, having to be subjected to our resources and our limitations, where they basically can do their own thing. Now, that was my last 5 seconds, so this is where I will stop. Thank you very much.
Great. Thanks, Eric. Looks like we have one quick question in the chat here, and that is, what are the most sustainable feedstocks you can use? And I guess just more generally, maybe, what are the feedstock-related considerations you should think about when you're deploying in your system?
Yeah, so the technology is agnostic. It is a liquid-liquid separation device. It is a liquid-liquid separation technology. So if there is a fermentation process that works, irrespective of the feedstock, our technology would improve it, provided A, there is a limitation, inhibition, product instability, emulsification, and B, it is extractable, right? If something is highly water soluble, for instance, ethanol, it is very difficult to extract it out from the water phase. You need a very large amount of extractant. The technology would work, but it becomes economically less attractive. Now, there is a specific feedstock consideration if there is a secondary feedstock, and that is, of course, that no matter how well you select your extractant, no extractant is 100% selective. It's not a zeolite or it's not an adsorption system. So since it is an extractant, an organic phase, you could also extract out an unwanted part of your secondary feedstock. For instance, a lignin-based feedstock can be rich in phenols, phenols being highly toxic to the microbe. In our case, we would remove, if you wish, clean up the dirty feedstock by removing the phenols, liberating the sugar, and having actually a very cost-effective process. Now, that's an example that we have concretely worked on with a client. But there are many other possibilities where the continuous removal is actually a side benefit of working with a cheap, non-purified sugar feedstock.
Hey, thanks, Eric, and very cool to see the progress with the aromatics. So with that, I think we'll
Thank
hand
you
it off to our next speaker, Toke Faurby from atSpiro, and he's going to tell us about how you can turn a shake flask into a bioreactor.
Right. So my name is Toke Faurby. I'm the CEO of atSpiro, and as Eric rightly said, we've developed the shake reactor that, in a nutshell, turns shake flasks into bioreactors. So what do we mean by that? We've tried to address a recurring problem in a lot of research labs, and that's really when you're going from the very simple, uncontrolled, early flask plate-based experiments to stirred bioreactors. There's a lot of people that are really struggling in that transition, and we've tried to take the best of flasks, being the simplicity, and combine it with the power of bioreactors, which is continuous monitoring and an automatic process control. So by combining these features, we've came up with the shake reactor that mounts on top of standard flasks and extends them with the capabilities of a bioreactor. And we see a lot of different applications for this through our research labs. And when people start using the shake reactor, we see that this increased capacity for high fidelity experiments really increases the overall efficiency of the lab in many ways. And there's a few key aspects that I'd like to highlight to begin with. One of the things that we're very proud about with the shake reactor is the simple setup. So a setup of the shake reactor is very similar to setting up a flask. It takes about 10 minutes. And I think one of the really important things about the shake reactor is that it's very easy to learn. So this is something that anyone in the lab can learn how to do in an afternoon. So it's really a flexible tool that makes planning and working in the lab much more flexible. Another important factor is that the shake reactor, it just extends the capabilities of the lab flask setup that you already have. So that it makes it really space efficient. It takes up roughly the same space as a 1 liter flask when it's in use. And when you're not using it, you can just put it away so it doesn't take up any lab space permanently. So it's a great way to upgrade the capabilities of an already established lab. The last thing to highlight is the automated control. So the shake reactor can automate a lot of the manual additions that needs to happen throughout our cultivation, leading to both better performance, but I think also importantly, again, saving time so you can manage more cultivations in parallel and get your results faster. So the shake reactor is developed as a general tool, and we have customers across both microbial and cell culture applications. The places where the shake reactor really shines is when you want to run quite a relatively high throughput, so you want to run in parallel, but there's also a lot of value to be gained from increased monitoring, increased data, as well as the automation and better control afforded. So places where we see a lot of success with our customers, it's applications such as material production due to the higher titers and yields. Applications like media screening and media development, where you get a much better insight into the metabolism of your cultures, as well as applications such as strain selection and strain characterization, again, where the increased throughput and more representative environment really makes the shake reactor a nice solution. Looking closer at how the shake reactor works, the shake reactor is compatible with 500 milliliter and 1 liter flasks, both baffled and non-baffled. So you get quite a nice range with the shake reactor. Throughout the experiment, the shake reactor is wirelessly connected to a unit called the BioHub. So this unit sits in the lab close to the incubator and provides real-time communication with the shake reactor. So that means you get your data in real time, and you can always send commands to the shake reactor or change or change the experiment if you need to. The shake reactor and the biohub form the lab setup or the equipment. And for each experiment, you need a set of single-use components. So the sensor module with the electrodes, sampling port, and steroid filter, as well as the 3 liquid containers for the dispensation system, is single-use. And this makes the shake reactor really fast and very reliable to work with. So you don't need to worry about cleaning, maintenance, or the lifetime of the sensors wear out during a run. The automatic dispensation is based on 3 50 milliliter containers that you fill during setup. So that means that you have complete flexibility in terms of what kind of feed or supplements you want to add, as well as any acids or bases. We use volumetric pumps. So it's essentially similar to a syringe style pump. That means we can provide a lot of features like automatic priming and automatic calibration. So as a user, you just put in the amount of liquid that you need for your experiment, and then the shake reactor will give you precise dispensations and precise logging. We also have integrated sampling ports. So the sampling port is part of the sensor module, part of the single-use component. And through lure lock ports, it's possible to sample from the system while keeping it closed, reducing the risk of contaminations. And it also makes it possible to sample from the shake reactor while it's still in the incubator, reducing the amount of time and handling that you have. To control the shake reactor, you set up different dispensation profiles that allows you to automate the additions of the shake reactor. These are collected into a recipe and sent to the shake reactor, which then executes it autonomously. To just show what that looks like, for instance, with pH, you would specify a time, a pH set point, and a tolerance. And by making multiple of these specifications, you can set up a pH profile with pH shifts or changes in tolerance. Feeding is much the same. So you specify a time and a feed rate in milliliters per hour, and the shake reactor will then do a continuous dispensation at that rate. And in the example, I've made an exponential feeding profile. Lastly, you can also do bolus or shot feeding if you want to add a volume at a particular time. But I think importantly, since the shake reactor is a connected device, it's also possible to do remote dispensation triggers, which is very useful if you want to do dispensations based on offline measurements. Classic examples are if you want to maintain a particular glucose level, or if you want to do induction at a certain optical density level. The data is available in real time through a web application, so you have access to this online. You can see this from anywhere if the data is on the internet, so you can see it from the office or even from the phone. And through our web application, you get access to the pH, dissolved oxygen, dispensation, and everything else that we measure. This is intended as a fast and simple way to view and review experiments. And if you want to do any more advanced analysis, then we have a simple CSV data export where you can get the data out in a standardized format. But through this data monitoring platform, you get access to a lot of the same information as you would get in a traditional stirred bioreactor. So you can see exactly how the pH and the dissolved oxygen curves trend and change together. And you can see how variations in dissolved oxygen correlates with changes in metabolism. And this really allows you quite powerful insight into the growth and metabolism of your cells and how they're growing and how you might want to change your experimental setup. So that's a quick introduction on the shake reactor. So I hope some of you are interested in turning your flasks into bioreactors. On our website, we have some white papers both on CHE.L and E. coli, and we're also happy to have your questions either now or in a follow-up call.
Thanks, Toke. We have one question in the chat. Is the shake reactor capable of supporting biomass hydrolysis or fermentation processes that require precise control of enzymatic activity and environmental parameters like temperature and viscosity? So sort of high viscosity processes, especially.
Yeah. So, I mean, we don't control the agitation or the temperature directly. So the setup of the shake reactor is that you would put it into an incubator. So I think the classical way of answering this question is sort of what does the existing setup look like? If you can use flasks, then you have a good chance of using the shake reactor. The shake reactor can take fairly high temperatures, but I think it depends a bit on the precise setup.
One question I had is around the dispensation profiles. So a very common profile that we use in fed batch is DO spike or DO feedback response.
Yep.
Glucose feeding. Is that possible in this system? Is that one of your built-in strategies?
So it's not built in yet, but we're working on it as a software update. So because we don't have the same controls as a traditional stirred bioreactor, we can't do the same sort of cascade dissolved oxygen controllers. So we need to think in how feeding affects oxygen consumption in a bit of a different way. But I think the short answer is that we are working on a way to do feeding based on dissolved oxygen, such that you can either maintain a particular level or just trigger a dispensation profile based on the dissolved oxygen readings.
Then I guess quick question. So where would you sort of draw the line and say, this process is a great fit for our system, or this process is something we still can't support in a flask, and you probably still need to go to the bioreactor?
So I think the key challenge for the shake reactor is that we don't have direct control of aeration. So I think very high cell density cultures, especially if you're interested in sort of the characterization and process development, is not the strongest suit for the shake reactor. So there are some of these microbial applications where I think the shake reactor isn't the right fit. So for microbial, I think it's better fit a bit earlier in the stage when you are doing strain selection and media screening, media development. And then on the cell culture side, it's much more widely applicable.
Great. Yeah, thank you, Toke.
Yeah, thank you.
Our next speaker is Mike Kobida from Caladan Bio. He's going to tell us about their modular bioreactor platform.
Okay, hey everyone. Mike Kobida, the CEO and co-founder of Caladan Bio. We are based in New York, in the US. We were founded last year, and we're bringing a new flavor to benchtop bioreactor experiments, in that we see biggest issues here being like lack of throughput, and that's a function of a few things, but the biggest will be mainly cost and just like ease of setting up experiments and running. So we're really focused on both lowering costs and also making the systems as simple and easy to set up as possible. So you can do that with basically like the minimal amount of labor and really increase the throughput of your lab. So we are we're holistically looking at the problem from both a robotics and hardware standpoint, but also in terms of data transportation and data analysis, as we see that all three of these together make up like total costs of running benchtop fermentation experiments. And, it takes kind of a holistic approach to actually, make a big difference in reducing cost and, building new tools. So our first product is the Caladan 250. So this is a 250 milliliter sort of like modular bioreactor platform that's designed to be high throughput, and that you can run 1 or up to 24 together on the benchtop, controlled by the same controller. You can break those up and run them, with like 4 different experiments in the same cluster. You can set them up to run with parallel feed lines, kind of like mix and match. And flexibility is really like the name of the game here, and that's what we set out to accomplish with designing the platform like this, where each reactor is kind of like its own system in itself, and they can be used as such. This also leads to the system being reliable and very serviceable, in that like one reactor, one piece can't like take down the whole experiment. So when setting out to design the system, we wanted to really rethink everything from the ground up, and so that included designing our own peristaltic pump system entirely, so that we have 4 individual liquid feed addition pumps. So those are peristaltic pumps that are designed to go really, really low on flow rates, so that you can pump continuously down into the like 0.01 or even lower milliliters a minute range. So that's like continuous pumping with a really reliable peristaltic pump system that's basically like very will hold values across like experiments, so the need for calibration is not like every single run. So trying to reduce that load as much as possible. Additionally, the entire system is heated and cooled with the Peltier thermoelectric cooling system on the tank. So that's a system that does not require an external chiller. So we can cool the tank down to 4 C or heat up to 60 C like very quickly throughout the experiment. Each reactor module has an integrated off-gas analysis system. So these are optical-based CO2, O2, and ethanol sensors, as well as temperature, pressure, and humidity in that same module. So that's located in each bioreactor module for continuous data of off-gas reading every second. Plus, like, interesting feature is that each unit is on its own set of load cells. So you can do things like mass totalization and tracking total volume of the reactor throughout an experiment. All of our feed pumps can be run both forwards and in reverse, so that it's rather simple to set up like a continuous or like chemostat fermentation setup. For the 250 ml system, we have both single-use and autoclavable tanks. So the single-use tanks are polycarbonate. They come with your standard suite of sensors, pH, cell oxygen, temperature, and those are completely packaged, irradiated, ready to drop in. There's no assembly required at all. And then our autoclavable tanks are 316 polished stainless steel. They come with pH, dissolved oxygen, temperature sensor as well. Those are fully autoclavable and designed to be fairly easy to clean and reset up. So a nice solution if you don't want to go down the single-use route. We really see the opportunity to build like a whole new platform around these bioreactors. And so one of the first accessories that we're working on is an auto sampler that will be available this year. So this is a system that will take 2 ml samples that will be stored in strip tubes that are in a cooling block. So that'll be cooled to 4 C. So you can take 8 samples with that strip of tubes, and then those strip tubes are designed to fit into an SBS plate, so that you can go put them inside a liquid handler or whatever your kind of like next step of analysis would be with those samples. Additionally, the tubes are easy to replace during the run while maintaining sterility. So you can take more than 8 samples throughout a run. In addition to the auto sampling unit, we're also working on a number of different features, like additional pumps. If 4 is not enough, we can add 2 or 4 more pumps in front of the unit, just like you see at the auto sampler now. Also load cells for feed bottles, stir bars, warming plates, a bunch of other small accessories to make this like setup as kind of like clean as possible to maximize the efficiency of bench space use. So in addition to the hardware, we're also working on a totally new, powerful software application. So that really is broken up into 3 parts, both experiment design, a run app, and an analysis set of tools. So our experiment design tool is kind of like a novel approach on experiment design. It's like a no-code interface that allows you to set up all your controls. So you can see in the top left here, you have a number of different points. So you can set an unlimited number of phases throughout the reaction. You can drag and drop around all of these points, and then between points, you can set that to either like a step function, a linear, increase, exponential, or you can define an equation to move between 2 points. Additionally, we have conditional control loops for standard things around oxygen cascading, feeding based on OUR, CER, things like that. And then we're also working on a tool that will allow you to take any of our measured inputs and use them to control any of the functions of the bioreactor. So you can really go crazy with like the amount of setup conditionally that you can do with the tool. The middle here is like the live experiment view. So seeing data throughout an experiment. It's a nice tool. You can customize all the charts. You can log in and see this remotely. You can access any of the bioreactor controls remotely through our browser-based interface. So that's all there. And then the last piece is like the analysis piece that is we're currently working on, where you can bring in data from any of your other analysis equipment, or from any of your sampling data, to get that all into one data set in a really easy, simple way before exporting. Another cool feature we're working on is we have an integrated camera into the unit itself. And so this is like our stainless steel tank. So this stainless steel tank is a site glass that is the whole entire vertical length of the tank. So you can see here what the view would look like, whether you're looking at this, from your desk, looking into the lab, or you can see this remotely if you're at home trying to check on things. Nice to have that camera there. And then also in Q1, we're releasing our like AI foam control. So that's using the camera to basically like dissect that liquid foam line and give you an actual foam measurement, and then use that to automate your NFOam additions. So that's all I've got. I'm happy to answer any questions. And if you have any more questions beyond this, feel free to reach out. It's just Mike at Caladan.bio. Happy to send you more information. Working on a few scale-up white papers that we'd be happy to share with you as well. Thank you.
Great. Thanks, Mike. I really like the idea of the AI foam control. That's a huge pain point. So I'm curious about one of our other pain points is, as we go to these kind of more multiplexed systems, things like sampling and induction and sample archiving become a big pain point as far as labor and people coming in at odd hours. Is that something that's on your radar, automating sampling or bolus additions of different things so that you can further reduce that labor requirement?
Yeah, absolutely. So we have this auto sampler unit that this is like a one-to-one relationship with each reactor. So you can pull 8 samples that get stored in strip tubes, and those are cooled. And then beyond that, we have a couple other products in development that are related to some, it's pretty cool, like high throughput sampling. features that we'll be releasing next year.
Oh, nice. Okay. And so you can go to, yeah, you can go straight to the plate archive.
Mm-hmm.
Cool. And what about scale up? Do you guys have any plans to allow folks to go to larger scales within the same ecosystem?
Yeah, it's definitely something we're thinking about. I think for the time being, we're working on a bunch of different scale-up white papers to characterize the system really well, so we can offer guidance if you're moving into systems from other vendors. But yeah, in the future, I think that's something I'm definitely very interested in.
And then I guess similar question to what I asked for atSpiro. Are there any kinds of applications where you think this design is limiting and someone might have to go to a larger scale or a more conventional bioreactor geometry? The things you just can't handle yet?
Yeah, I think this is actually something we're actively working on, is specific solutions for filamentous fungi, some of the higher viscosity strains, and that the reactor this small. I think there's some issues that just like arise that because of the size of the probes relative to the tank and things. We think we can do a lot better, and it's something we're working on.
Great. Yeah. Well, exciting stuff. Thank you, Mike. Please feel free to add any additional questions for Mike in the chat here.
Yeah, that's good. Thank you.
Our next talk is Rich Waller from the H.E.L group, and he's going to tell us about different application in high pressure fermentation. So Rich, if you're on, I'll let you take over this.
Awesome, thank you. Okay, well, good morning, good afternoon, good evening, everybody, wherever you are in the world. My name is Rich Waller. I'm the product manager here at H.E.L Group, looking after our biotechnology solutions. And today I'm just going to be telling you about how pressure boosts biomass fermentation efficiency. So just before I dive in, just to set the stage, I'll be discussing who we are as H.E.L, who we help, the key challenge that we are solving in this industry, who we've helped and how, and then discussing a bit further about our biomass fermentation solution. So H.E.L Group, we are a scientific instruments company based in the UK, just outside of London. And for nearly the last 40 years, we've been developing research tools to support and empower scientists across various applications, most notably for this talk in biomanufacturing, utilizing our automated bioreactor systems. And we've got nearly over 2,500 systems installed worldwide. Just a quick map of where we are in the world. So we are wide and far, with offices around the world and distributors, including offices in the US. Okay, so who we help? When it comes to our biomanufacturing technologies, we have focused primarily in some key markets with organizations working across biofuels, sustainable aviation fuels, syngas, alternative proteins, vaccines, and green chemical or polymer synthesis across various stages, from academia to process development, scale up, and more popular these days, scale down. Where are we today in the biomass fermentation industry? So with everything around us, everything is wanting to become greener and more sustainable. And how are we doing that? Well, firstly, a lot more sustainable feedstock focus has been in the limelight. So looking at using CO2 and other waste byproducts as feedstocks over more traditional methods, such as corn syrup or fructose. Secondly, looking at decarbonization, as most organizations and nations are looking to reach their green targets. And so CO2-based bioprocesses or biomanufacturing is becoming more and more of a demand and mandated by government. And with that, a lot of circular carbon feedstock focus is now coming into play. Lastly, looking at the carbon conversion efficiency. So with going green and the noble effects of all of this, we do need to face the reality that some of these processes are incredibly expensive and the results aren't as what we would expect them to be. So how can we get more bang for our buck? Going on from the trends, looking into 2025 and beyond for the biomass fermentation industry, what is of key importance? Well, high yield and high titer, I think that'll be there above and beyond and always on the list. But most importantly, that's becoming more and more valued in industry is utilizing sustainable carbon feedstocks, as well as looking to maximize volumetric productivity. So how can we make more with less? And I guess the question that we need to be putting to ourselves is, how are we going to achieve these requirements? Well, there's many factors that we need to consider, but the two most important ones that we've come to see is obviously selecting a high productivity strain. So is your microbe able to deliver the goods? And secondly, are you looking at how your fermentation method and monitoring your method and how this is impacting your titer and volumetric productivity? So at H.E.L, with our biotechnology solutions, there's a key challenge that we are focused on solving, and that is maximizing titer and volumetric productivity with high pressure. What does this enable you to do? Well, gaseous feedstocks now become an option in your arsenal, in your productivity and your process. And combining that with high pressure, we're able to do a very simple thing in increasing gas transfer, and combining that with our automated gas control software that ensures safety, but most importantly as well, ensuring that the gas feedstock is replenished based on normal metabolic consumption. And where that leaves you is higher substrate availability for your high productivity strains. Obviously, this has a number of knock-on effects downstream, but where we're able to offer this solution is through our BioExplorer. So to introduce the BioExplorer to you, this is a high-pressure automated benchtop parallel bioreactor. And we have been playing with high pressure and parallel reactors for nearly 40 years. And if you'd like, there's a QR code on the screen. So if you want to scan that with your phone very quickly, you can see a 3D render, and you can check it out in your lab or your living room or wherever you're watching this from. And we'll dive into the specs around this piece of kit a little bit later on. But who have we worked with this bioreactor? A host of different innovators, just a few on here, and this spans industries across biofuels, chemical synthesis, alternative proteins, and vaccines alike. I want to just share with you very quickly a little study that we were able to look into, whereby if we zoom ourselves into France to an institution called INSA Toulouse, there's a professor there who was looking at investigating using an engineered autotrophic strain if they could create high gas transfer to reach high biomass, but also isopropanol titers in the grams to liter range, utilizing CO2. So when they approached us, the setup that we were able to provide was our BioExplorer 400P, which was the piece of kit you saw on the previous slide. They were working with around a 330 ml working volume, and they were able to utilize a host of different gases, including carbon dioxide, hydrogen, nitrogen, and air. And they investigated two different gas feeding routes. I'll focus on the second route for the case today, but essentially what they were able to do was flush the headspace with nitrogen and then have 3 individual gas sparges placed in the medium, delivering the air, CO2, and hydrogen. They also had some off-gas analysis utilizing another piece of kit called the tandem gas analyzer, monitoring CO2 and O2. So diving into the results, I've created a little table here just to summarize exactly what happened. So if we look at the bottom row, Algarix et al. 2020, they were using a strain called C. nicata, and there were some slight metabolic enhancements. And they were using, obviously, CO2 as a feedstock to generate isopropanol. They did this at varying pressures up to 4 bar, and they were able to generate a final yield of isopropanol of 3.5 grams per liter. In the paper, they were comparing this to another well-regarded paper by Grossau et al. 2014, where they utilized a very similar strain. It had further metabolic enhancements to ensure that the movement of carbon from feedstock to final byproduct was further enhanced. And I think it also was not as inhibited in terms of growth when it was exposed to isopropanol. They were using a normal bioreactor, normal pressures, and they were able to reach around the 3.5 gram per liter mark as well. So the story that I'm trying to paint here is, with pressure, we're able to utilize gaseous carbon feedstock forms, and under high pressure, we're able to achieve comparable results to traditional fermentation methods. If you'd like, I've got 2 QR codes at the bottom of the screen. You can scan those, and it should take you through to the papers if you want to go and read these for yourself. So I'll give you a few seconds to do that. Otherwise, at the end of the talk, my email's there. You can pop me an email, and I can share the papers with you if you do hit a bit of a paywall. Okay, what is the BioExplorer and what does it offer? So, bioreactor that's got traditional liquid feeds, and we utilize very high resolution peristaltic pumps for very accurate feeding. As we know that when you're working at smaller volumes, this is of great importance. We've got, different types of traditional stirring and agitation, different types of reactor materials available from glass to stainless steel. We've also done some special projects using H.E.L and other tantalum coatings, depending on the types of corrosive or very acidic or basic mediums being used in the fermentation. Most importantly, we've got our gas feeds that are delivering gas at a very controlled rate for a number of different gases. Our vessels, which are pressure rated up to 10 bars, and we've got a pull through all the way through to 5 liters, so offering scalability from 120 mils all the way through to 5 liters with our 5000P. And with this, with both pieces of equipment, you're able to have varying probes for whatever your processing needs and whatever your monitoring needs are, from level sensors to dissolved oxygen, pH, and optical density. So the 3 core benefits that we are able to offer within pressurizing biomass fermentation is that through generating superior gas transfer, automating processes with our powerful software that allows you to design very bespoke recipes and very customizable to the exacting needs of your process, and allows you to play around as well, and having that flexibility, as well as built-in safety controls that ensure working with pressure and maybe the mixing of oxygen and CO2 or hydrogen, things can go bang, but we ensure that that never happens because we've got the controls in place that can downgrade risks very rapidly. And lastly, the ability to create bespoke configurations for head plate designs for the reactor vessel. So depending on whatever your processing needs are, you can have the different types of probes, feeds, gas feeds, and sampling needs as well. So where I would like to leave the talk today is there's an opportunity in this industry to unlock productivity, and we can do that through utilizing sustainable feedstocks, such as circular carbon feedstocks that are cheaper and widely available. There is a greater availability for your microbes to do what they do best, especially if they've been selected for high productivity. And lastly, maximizing the productivity for the volumetric productivity and creating more with less. And with that, if you'd like to learn more about any of our solutions, please scan the QR code to book a call to learn more or get any other additional information that you may like. Also, my email is there at the bottom if you've got any other specific questions or would like access to some of the papers, please feel free to reach out. Thank you.
Thanks, Rich. We've one question in the chat. The question is your system compatible with hydrogen gas supply?
Yes. I'm pretty sure we had, yep. So in this experiment that we used, hydrogen was utilized.
Yeah, thanks. I've got a question on pressure. This is something that's in interest to us as well. So what's the highest pressure that you've been asked for in your system? Is there demand to go all the way up to the max pressure that your system can handle?
Yeah, there's some very interesting custom projects that come through. I know 40 bars has been flown around and 100 bars has been entertained. I would need to double check on that, but I do know that there are quite a lot higher pressures that we could definitely go to, but 10 bars is a very safe range for this piece of equipment. But if it were to be explored to go higher, we could definitely investigate that more. And I think we have done higher pressure projects. And we obviously take into consideration the safety risks, but yes, it is a possibility.
Wow, okay, 100 bar. That's a lot higher than I expected.
Yes.
We've heard rumors of such things for subsurface microbiology or looking at creatures that grow deep under the earth.
Yes, exactly. Yeah, there's a host of different high pressure applications outside of, I guess, biomass fermentation, but yeah, very, very interesting worlds out there.
Yeah, thanks, Rich, and thanks everyone for joining for this early morning session, at least for those of us on the West Coast. I'm going to kind of continue in the same vein here as Rich's talk about some applications we have at ABPDU using actually the same system he's describing for pressurized and gaseous fermentation. Let me pull it up here.
Eric, there was one thing I forgot to mention, if I could just throw it in quickly. A colleague of mine and I were just doing the numbers between the two papers that I mentioned above, and we were looking at the costs per sort of gram of, I guess, fructose and CO2 utilized in each process. And when we looked at it, we were able to see that when obviously there's a host of different variables involved as well, but just looking and focusing in on the substrate or feedstock usage, there was about a 60% reduction in cost, just purely based on the difference between using fructose and CO2, which we thought was quite interesting.
Yeah, it's very interesting. It's something we've seen as well, especially as the prices of some of these gaseous feedstocks are continuing to decline.
Exactly. Yeah.
With electricity costs. Yeah, so I'm going to talk you guys through some applications for these gaseous and pressurized fermentations that we've done at ABPDU, and this is very in line with what Rich was just describing. So I'll start off. We had some questions yesterday about the distinctions between some of the different DOE programs in this space. So just kind of wanted to run through how ABPDU fits in that ecosystem. We really specialize, of course, in process development and process integration and scale up. there are a number of synergistic efforts at Berkeley Lab, including Joint Bioenergy Institute and Agile Biofoundry, both of which are in our building. JBay focuses heavily on more basic science, pathway discovery, and biomass to biofuels conversion. We work with them a lot to help raise the TRL of those processes. Agile Biofoundry is almost kind of a sister program within the Bioenergy Technologies office at the Department of Energy. And the focus there is really more on the organism side and accelerating these design, build, test, learn cycles. But of course, process development is a big part of that test and learn portion of the cycle. And so we are a capability that can be leveraged via both of these programs for those who are interested in more on the organism side. So our capabilities range, as Deepti was saying, from 250 mil sartorius amber fermentations up to 300 liter. So we have the amber automated fermentation platform. We can do piloting. We can do process development at 2 liter scale. And then we've also invested significantly in gas fermentation, which is what I'm going to tell you about today. We've leveraged these across now more than 85 industry partnerships, more than 25 academic partnerships. So we've kind of seen it all as far as different processes, process configurations, organisms, feedstocks, products, anything that people are going to throw at us. We've used these to kind of stress test all of our systems. And the reason we're so keen on gas fermentation, similar to what Rich was just describing. So there's this whole host of low-cost feedstocks that can be unlocked via gaseous bioconversion. Some of these are electrochemical feedstocks, which are benefiting from a massive decrease in the cost of solar and wind power alongside significant investment and decreases in the cost of the electrochemical systems to produce things like hydrogen and formate, which can be used as biochem feedstocks. Of course, utilizing carbon from ethanol and other facilities is a major value and can really increase the yield that you can get from your biomass feedstocks. Anaerobic digestion is also on the radar, so it's another way of funneling biomass and wet waste into single carbon gaseous feedstocks that can be converted alongside gasification, which plays a similar role. And then there has been a lot of interest as well in things like flared natural gas and industrial waste gases. So these are fossil carbon sources, but these are fossil carbon sources that are currently just burned. So we can certainly be doing better with those. And these can be converted into the whole suite of bioproducts that are accessible via sugars. So fuels, polymers, foods, anything that can be produced from sugar can at least theoretically be produced via pathways from single carbon gaseous feedstocks. So the problem that we identified fairly early on in this space with regard to process development, one is that if you think a shake flask is bad for a heterotrophic process, a serum bottle, which you can see at the bottom here, is even worse, much worse, because it has a finite gas supply, variable pressure throughout your run as that gas is consumed. And you can only put a certain amount of gas in there, which limits the cell density of your process and has no controls at all. And yet these serum bottles are kind of the standard for what people are doing at small scale in the gas fermentation space. And part of that is that as you go up in scale, you're dealing with things like flammability, pressurization, gas toxicity, and these are barriers to operation. And that's compounded by the fact that there's very limited off-the-shelf equipment. So actually the H.E.L system that was just described was, at the time of our procurement, the only system that was available to handle these feedstocks. And so if you wanted to go to a CMO or a CRO to develop these processes, you really can't. There's nothing out there. And there's also nothing out there as far as best practices for scaling these things up, because a lot of that is a lot of the scale up and high density cultivation conditions are kind of behind the wall at these companies. And one that I'll add, which is kind of my personal crusade more recently, is that you would never think of running an aerobic fermentation without a DO probe. And yet we're running all of these gas fermentations without a hydrogen probe. We don't have a dissolved hydrogen sensor. We don't have a dissolved carbon monoxide sensor. These are critical parameters where we're just kind of flying blind. So, if anyone has leads on technologies for dissolved gas monitoring in that space, we would be very keen on looking at it. And so our goal was to really start to develop a more accessible facility to run these kinds of processes. And so you can see what we have here. We have the 8 by 500 mil H.E.L. Bio Explorer system that Rich was just describing. We also have a 20-liter scale-up reactor. These can be run up to 5 bar. The limit at the moment is just the pumps. So if we want to go even higher, we need to replace those peristaltics with higher pressure pumping. But that's something that's been on our radar if we see more applications in that space. And then we also went out of our way to equip it with basically any gas that you might want to use. So hydrogen, methane, oxygen, CO2, CO, ethane, nitrogen, air. Any gases can be provided in any combination to accommodate kind of anything in the application space. And then any of it can be analyzed via our micro GC off-gas analyzer. So we can measure not just CO2 and O2, but also methane, hydrogen, CO, anything we're supplying, close that mass balance. In our larger system, we now have a hydrogen generator going in. So we can put 20 liter per minute of hydrogen in there that's generated continuously via electrolysis. It means we don't run out of gas and we're not dealing with large volumes of flammables. So just a couple examples of where we've applied this. First one here, this is a project we have with Checkerspot, and they're making human milk fat analogs from sugar using oleaginous heterotrophic algae. So they're making this from sugar. But one of the things we wanted to assess here was that there are scale-up variations for heterotrophic processes that have to do with pressure. And that's because larger scale fermentations have hydrostatic pressure at depth. And so we were able to use this system to develop an accurate scale-down model for their large-scale process and reduce variation from a half liter to 300 liter to less than 10%, which contributed directly to the success of their runs at larger 1,500 plus liter scale, and to the release of their successful release of their product. And this was done in combination with Biomade and UC Davis. We have other projects with gas fermentation developers, including Industrial Microbes, Cerillo, and Windfall Bio. We've also used this to support fundamental research. So on the left, we're running acidophilic and thermophilic microbes in this system that are utilizing formate and hydrogen in a combined fashion. So it really pushed the boundaries of what the system can provide. On the right, we used it to assess direct uptake of CO2 from the atmosphere in Cupervitas Necator. So there we're actually able to strip CO2 directly from the atmosphere at atmospheric concentrations. And that's something that's only possible with continuous gas supplies and hydrogen as the energy source. We've really pushed the limits here as far as achieving high dry cell weights. So we've managed to get dry cell weights of up to 25 gram per liter. In this case, this is an organism, Hydrogenophaga pseudoflava, that is an aerobic carbon monoxide utilizer. And so this is an organism that had previously never grown beyond about 0.1 gram per liter. We used this system to push it all the way to 27. So 200 times higher than what was reported in the literature. And that's done entirely with carbon monoxide as the sole carbon source. And so this is really a unique platform in that primarily carbon monoxide conversion is done anaerobically. We've also looked heavily at integrated biochemical electrochemical reactor design. So this is actually somewhat similar to what Martin was describing earlier. We've been looking heavily at electrochem integration and ways that we can do process development with electrochemistry in the same cell and do some kinds of process simplification and consolidation. So in this case, what we're doing is direct electrolysis in these glass bioreactors, where we're replacing any gas sparging with direct water splitting and supplying only CO2. And we can see that with no current to the cell, we don't get any production. When we apply current, we can get cell densities up to a very reasonable level. And we can also express production of flaveolin, which is a surrogate molecule that we can express heterologously to assess whether we can produce non-native products in this kind of a system. We've since expanded that to include in situ formate generation as well. So formate can be produced in situ from carbon dioxide. It's a way of essentially directly recycling the CO2 in the system by reducing it electrochemically and then consuming it biologically and generating biomass from electricity using these unique fluidized cathodes. So these are actually, the cathode is actually dispersed on particles throughout the system. So this way we can actually recycle the CO2 in situ and essentially reuse all the CO2 to achieve 100% carbon uptake. And integrated system testing for this is ongoing, and I think it's actually just concluded successfully. So we're very excited about that as well. So I'll leave it at that. Just a big thanks to the ABPDU team, and big thanks to our morning audience here. And I'll take any questions before we go to our first break.
Welcome back, everyone. So in this session, as I mentioned earlier, we're going to go over novel equipment in this space, equipment that can help with bioprocess scale-up. So our first speaker, Bruce Lee from TJX Bioengineering, is ready to talk about the bioreactor that they are offering, bioreactors.
Okay, thank you for the introduction. My talk is not actually directly about our products or services. We already have happy customers like OWI from Paul Bell yesterday and Johannes from Boston Bioprocess today, who just presented. So at the end of the last session, so they are using our benchtop and pilot reactors for their mission critical tasks. So there's nothing more that I need to say. So I'd use this opportunity to share something that I believe is of broader interest. In the past few years, there has been a surge in biotech startups, particularly in the precision fermentation space. This growth has been largely driven by increasing demand for sustainable and alternative protein sources as food and feed ingredients. And for these fermentation products to be economically viable, the size of each bioreactor that produces them needs to be in the 100 cubic meter range. And this is determined by manufacturers like the CapEx, OpEx, market demand. So it's not something that can be easily worked around. But unfortunately, based on my interactions with many of the startups, it seems bioreactor scaling up is frequently overlooked. I mean, today and yesterday's theme is like, I can hear a constant theme that everybody's saying scaling up is difficult, it's hard, but this is actually not seriously considered until a much later stage by the startups. Many of them have the impression that it's just engineering, or you can get those large-scale reactors off the shelf and it will work. So in reality, bioreactor scaling up is extremely complicated and it requires a lot of effort from early on. The textbook approach for bioreactor scaling up is to enlarge a small-scale reactor in a geometrically similar fashion. So you keep all the proportions and make it larger, make it bigger. Then the agitation speed is determined by based on an eco-specific power input basis, or is also called power density, measured in watts per cubic meter. So why the power input is important? The mechanism underpinning this approach can be explained by invoking the Kolmogorov microscales, where the mixing and mass transfer are related to the energy dissipation rate in the system. So in other words, bioreactor design and operations affect the bioprocess through this parameter. It's like the central parameter that determines everything. With that in mind, the average energy dissipation rate is the agitation power divided by the liquid mass in the tank. The volume and the density of the broth normally are already given. We can get those from the small scale experiments. So all we need to do is, when scaling the bioreactor up is to figure out the power input from the agitation system. To do this, there are highly reliable empirical correlations for estimating the agitation power, at least in the turbulent flow regime. So if you believe in this approach, this is only equation you need to scale up your bioreactor, because the size of the reactor and the shape of the reactor is just directly in an enlargement from the small one, and then all you need to do is to determine the agitation speed of the large reactor, and it has a relationship with the diameter ratio between the small and large reactors. It looks rather easy, right? But the problem is you cannot scale every parameter proportionally. At the same time, you can keep one consistent, but you cannot maintain all of them. And one example is the aeration rate, or VVM, volume of gas per volume of liquid per minute, and the superficial gas velocity. See, the VVM is the volumetric gas flow rate divided by the liquid volume, and the superficial gas velocity is the volumetric flow rate of gas divided by the cross-sectional area. So if you keep the VVM constant, and the superficial gas velocity will increase proportional to the reactor height. To the reactor height, the bigger the reactor, the higher the superficial gas velocity, and this has direct impact on the gas to liquid mass transfer, and which will affect the OUR, the OTR, and everything. So another example is the mixing time. So even if we keep the pore density or dissipation rate constant, the mixing time will still increase exponentially with the reactor size. To look at it in another way is, if we want to maintain the mixing time, we keep the same mixing time across scales, the power input will increase exponentially. And then that will kill the economics of your process. It's just too costly to operate. So there is, in fact, a very narrow opportunity window for a successful scaling up. It's very narrow. We must consider multiple competing factors at the same time. As you can see from this diagram, there is basically a wall in each direction. As I just mentioned, mixing will definitely get worse if we increase the size. If we increase the size of the reactor, it's inevitable. If we increase agitation in order to reduce the mixing time, mass transfer gets too good. It can get too good, and the carbon dioxide partial pressure will increase. Or in some cases, if you increase the agitation too much, then there's too much shear. So in order to bring down the CO2 partial pressure, you may think we increase airflow, but then there will be too much foam. So this can go on, and we are really confined in a very small window. One case study here. So in an ideal world, when we scale up a process, we want to keep every parameter consistent. But in reality, you are lucky to get a single most important parameter consistent. And that's why at the end of last session, I asked Johannes, did they see the performance degradation when they scale beyond 1,000 liters? So I once worked with this client, and they successfully in-house, they did this in-house. They successfully scaled from a 5-liter lab reactor by 1,000x to a 5,000 liter pilot reactor. And the performance was the same. It was consistent. So they became very confident and designed a 300 cubic meter commercial scale or production scale reactor based on the same principles as the textbook approach. But it was a disaster. Long story short, they only got half the performance. Yield is halved, and the productivity, the time space productivity grams per liter per day is also halved. And then I performed some CFD analysis for them and showed them that the only parameter that's consistent across the 2 different scales is the dissolved oxygen, and which is 0. So it is 0, so you don't really know how much it's likely, because it cannot go lower, right? And all the other parameters, like the superficial gas velocity was more than 2 times higher, KLA is more than almost twice as high. And the partial pressure of carbon dioxide in the winter gas is actually too high that the winter gas analyzer cannot output the value. It's beyond the maximum value. And the power consumption, the power density is actually lower. It's less than half. Mixing time is more than 3 times higher. So this is a real case, real life case study. It was not easy. We eventually solved the problem by modifying the spider of the bioreactor, of the larger bioreactor. But you can see it's nothing like geometrical scaling up and keep everything or something constant. It's more than that. So CFD simulations can tell us those differences. This does not really require much more information from on the biological side, but the CFD simulation itself does not know the culture's response to the differences. So to get that answer, there is to gauge your culture's response. There is a method called a scaling down model. I saw a few people mention this, but they didn't really go to the details. Well, the idea is with scaling down model is we try to mimic the environment in the large scale reactor at the lab scale. So we can have multiple reactors, small reactors in series, and we circulate the broth between them, and then one of the reactor may be similar to the bottom of the large scale reactor, the other one is similar to the top. Or we can have a single reactor, and then we oscillate the operating parameters. We can have airflow goes up and down, and agitation goes up and down, and see what happens to the culture. And this idea of scaling down leads us to the ration approach for bioreactor scaling up, where modeling and experience is of critical importance. You perform your experiments, you feed the data in a model, statistical or mathematical or first principles, and then you get your ideas by looking at the model, outputs the simulations, and then you iterate. You basically need to iterate, and then from there you can probably build 1 or 2 different scales of the pilot, and then we go to the industrial scale. Now here I just summarized what I just said. While this ration approach, it can maximize our opportunity or our chances to success, it's a long, costly, and iterative process. And unfortunately, most startups lack the expertise, the resources, or they simply do not have the time to do it in-house. Us and with our partners, we can help. So if you want to continue the conversation and see what we can do, here are my contact information. That's it. I think I only have like 15 minutes.
Thank you, Bruce. I don't see any questions in the chat yet. I guess they will start now. In the meantime, very quick question from my end, and maybe you mentioned this, but if you could re-mention. These reactors that you have and the scale down models that you're talking about, they're applicable to all microbial systems? E. coli, yeast, fungus?
Yes, the approach is the idea behind this is general, is of general applicability. So it some may be more sensitive, like some cultures may be more sensitive to mixing or gradients in pH or temperature or dissolved oxygen. Some may be less sensitive, and that's why you need to test it. So, but the methodology is the same. It applies to all the different cultures.
Got it. Any other questions for Bruce? If not, we can thank Bruce for your time.
Thank you.
Thank you very much.
Bye-bye.
So next up, we have Jared. Jared, are you available and online? There you go. Yes.
Yes, I'm here.
Hi, Jared. So Jared is from Scientific Bioprocessing. You could share your screen now, Jared.
Yes, absolutely.
And Jared is going to talk about how to make your shake flasks perform like reactors.
All right. Can we see the screen that I'm sharing here?
Yes.
All right, awesome. So hello, everybody. As Deepti kindly mentioned, my name is Jared Trefz. I'm a technical specialist and account manager here with Scientific Bioprocessing. I'm just going to present on some data that we have for some shake flask translation to reactor data. So who are we? We're a company that develops sensors at the small scale. You can see on the left, we have the shake flask scale and our sensors associated with that. And on the right, our bioreactor scale as well. For today, we're just going to focus on the multi-parameter sensor, our dissolved oxygen sensor pills, our automated feeding system in shake flasks, as well as our older legacy technology, which is our biomass monitors or cell growth quantifiers. And on the right, what we're not going to focus on today, but still features of, what we produce and what we develop are our biomass sensors for bioreactors, for glass reactors specifically, our flow cells for pH and dissolved oxygen monitoring in perfusion systems mainly, our flow loop systems, and then of course the BioR Pro, and that's really just a smaller format of the cell growth quantifier BioR with some increased capabilities for smaller single-use vessels such as that of the Amber. So what is the presentation and why are we really developing this technology? So what we've observed in the industry and a lot of what we're trying to develop is giving the power back to a lot of scientists at the shake flask scale. So we've seen there's a lot of optimization at the microtiter scale, a lot of optimization at the bioreactor scale, and this mid scale that these two converge on, the shake flask scale, has not had much development at this point. So we want to develop something that has more reliable and consistent data with online monitoring, something that you can use for those final phase strain developmental insights and early phase pre-developmental bioreactor insights, and something that we can really, give to scientists and engineers that free up their time from a laborious sampling perspective or preparation perspective, and just be able to draw insights from the scale that we previously didn't really have visibility to, especially when we were converting a lot of our cell lines from shake flask to bioreactors. And so what we're going to run through today is some data developed by our senior scientist here at SBI. I can't say enough good things about Christina Dickmeis. So she is our senior scientist and she's on the chemosensor development team in our R&D group. She's a master of fermentation and she's really driving a lot of the application-based growth and development on our new sensors that we're going to have some of a presentation on today. So thank you to Christina, who is unfortunately not able to attend because she's probably getting ready to go to bed right now in Germany. But nevertheless, I want to make sure I give credit where credit's due. Looking into our use case here, so the production of glucose oxidase in Pichia pastoris, where we're going to start is just giving you an overview of the experimental design that we have. So what we did is we had a Pichia pink strain from Invitrogen with a glucose oxidase variant integrated into the genome. And then you see here our general experimental setup. So we have our 25 mil BMGY medium, and then we also have our, at least for the shake flask, relative to a reactor 1.5 liter, and then the different conditions that we're going to have in both. These were really drawn from literature. So what we wanted to do is take use case from literature and just be able to present that and improve on that use case with our technology. And so what we see here on this next slide is just kind of a standard look or view into what you can see in a reactor process that we pulled from literature. So you're going to have your typical batch phase that I think we all know, as well as your fed batch and starvation phase in the middle here, and then your typical methanol induction phase as well. And so really driving points home around this is just that there is a reason that the reactor is the state-of-the-art scale and technology for bioprocessing production. And so at every phase, you're going to have all the parameters you need to monitor, and then the process controls you're able to monitor as well. In this case, we were able to use our CGQ BioR to monitor biomass on the actual reactor itself, which is a mini-force reactor, a 2-liter mini-force reactor. And as you can see here, just kind of the standard phases, starting with batch, seeing that starvation, and then conversion from glycerol to methanol induction for that automated methanol induction feeding. And so the next slide. The next slide gives an example of what we pulled from literature for Pichia pastoris design of experiment or experiment in shake flasks. And so as a standard shake flask, you really see here, there's quite a bit of limitation. You just have your standard batch phase and then your methanol induction, which called for a shot of methanol every 24 hours in a shake flask. And so what we did with this use case is we've really built it up over time, including our legacy technology. And the first place we started is with our older biomass sensor and liquid injection system. And so what we did here is we kind of integrated that into the mix to really see how we could optimize this with our legacy technology, because at the time, that's really all we had. And so what we started doing is we looked at a lot of different aspects of how to improve the process. So feeding strategies you see on the right here, that multi-shot every 24 hours, but now automated with our liquid injection system, a single shot delay and constant feed that was really relative to what the reactor literature constituted. And then of course the constant feed as well to throw a third variable in there and see how it performed. But we evaluated all of these things, time point for induction, the amount of methanol we were intending to feed, buffering the feed to see improvement there, the fill volume that was optimal for the shake flask scale to increase production, and then of course the adaptation time from glycerol to methanol. And so we came to the conclusion here. I'm not going to go through every single little detail of, exactly what we came to the conclusion of, but there's a 10% fill volume with a 500 ml flask, a certain amount of methanol at different concentrations that we found optimal, and then an actual triggering point for that adaptation from glycerol to methanol, starting at a growth rate of around, 0.002 hours. The 7-hour adaptation time, that's something I'll kind of touch base on a little bit more later, but there is relevance there in terms of a translation from a flask to reactor insight that we're even able to pull just with this older technology. And so what the process looked like beyond that is we really come into a point where we're starting to see a little bit more improvement at the shake flask scale with what's possible from a process automation and improvement perspective. So now during our batch phase, we do have the ability to monitor biomass with our older technology. Unfortunately, the liquid injection system only has one feed. So we had to skip the fed batch and starvation phase because we're going to use that feed for the methanol induction phase. But at that phase, we were able to have that adaptation shot of 1% volume by volume of methanol and have that conversion from glycerol to methanol, and then a constant methanol feed to really optimize or increase the yield of the production of glucose oxidase. And so this is the result of the most ideal delivery of how we could optimize this in a shake flask. So the most ideal profile was the single shot adaptation with a constant feed of methanol beyond that. And this growth rate in gray here just shows kind of where the trigger initiated. And then the blue line on the graph is going to be your biomass. You can see, gradual increase until it hits that stationary, triggering that growth rate feed of the methanol. And then we have a conversion set point for the adaptation time and overall production, or I should say induction of increased methanol dispensing. And so overall conclusion on this older technology is that we did see about a 10-fold increase just using this older technology to try and optimize the experimentation just with the biomass and the growth rate. Still things to be improved upon, which we'll allude to a little bit later, but just as a general summary, it took about 26 runs to execute this, around 200 liquid injection cartridges. And then for a senior scientist like Christina working with a project like this, while she has the main objective of developing new technology and applications for our sensors, it took around 3/4 of a year to execute this. And so what we're really trying to do here is just constantly push the envelope on more insights that you have added to these sensors and how they're going to improve the process, design of experiments, and intuition of your scientists and your performance or results. And so what we have here is just an example of the platform we've recently released. And this is really the next generation of our sensors that we have. So we still have the liquid injection system as our main feeding module, but on the bottom left here, we see our multi-parameter sensor. And so with this new sensor, we're able to monitor biomass, fluorescence, dissolved oxygen, and more parameters like your standard incubator parameters, such as humidity, pressure, and things of that nature. And then we also have our DOTS software. That's just our software that we use to monitor everything from our bioreactor sensors down to our shake flask sensors, as well as these sensor pills. And these sensor pills are really a concept that we developed to be able to improve parameters within the same sensor. So you can see here we have dissolved oxygen right now, pH coming soon. It's a format or a technology where the sensor works with the chemosensor dyes on these pills to be able to garner these measurements. So in the future, just like we have dissolved oxygen pills to help assist in measuring dissolved oxygen, we're also going to have additional pills to help measure pH, even glucose inline sensing we're working on right now as well. And so this is just kind of a look at the sensor itself. I'm not going to run through every little detail, but I think it's just good to conceptualize and understand what the technology is and how it breaks down. So a couple of different aspects here. Mainly what we're focusing on today is the backscatter aspect, which is your biomass aspect, and then the dissolved oxygen aspect and how they work in tandem with the liquid injection system from that PID controlled feed perspective. And so revisiting the use case here, we wanted to push this even further with the multi-parameter sensor and the liquid injection system. And so what we wanted to start with is we just wanted to take where we left off with our older technology when we didn't have a leading indication of how the metabolism was performing. And we just wanted to look at how the dissolved oxygen behaved with the preset profile we had, which we had no insight into. And what was really nice to see is that we do see that the dissolved oxygen responds quite well to these different feeding steps you see in light blue. While we were off maybe a little bit with the adaptation phase you see here initially with the initial trigger of the methanol feed. And I guess I'm going to use the laser pointer here. I didn't even realize, but right here is where you can see, the adaptation phase maybe required a little bit more time. But beyond that, when the cells were fully adapted, we see really good recovery from this dissolved oxygen, almost matching up to what we anticipated with our legacy technology around the optimal feed profile. And then beyond that, what we did is we integrated this PID controlled feed loop to also confirm the amount of methanol that was fed is about relative to what we predicted initially. And so what we see here is we have around an 80% set point that we set after that initial adaptation shot was given. And so that 80% set point really provides the ability for the cells to recover and for the PID controlled feed on the liquid injection system to know when to inject the liquid back into the flask when the cells have used up the methanol that we've initially injected. And on the right here, you can kind of see here, our initial prediction on the DO-based feeding is pretty much relative to the DO-based feeding, or sorry, our initial projection here, our initial volume dispensed on the biomass-based feeding is fairly relative to the DO-based feeding. Again, validating kind of the design work we did before, but also really good to see that even when the cells are dictating the feeding themselves, it's pretty relative. And so from there, we wanted to look at what else we could improve at this scale and what else we could improve that might, have an effect on the overall yield, as that was really the main objective here. And so the next thing we looked into is how would fed batch applications or a fed batch phase really affect this? And so we modified the overall workflow to now look something a lot more like a reactor than what we saw in the initial use case, especially with the standard flask without any sensors attached to it. And so what we have here is we have kind of our standard batch phase. We now have biomass and DO monitoring, missing that pH and antifoam, the glycerol fed batch phase and starvation phase. So we had that constant glycerol feed, no pH maintenance, but also that starvation phase at the end here. And then of course our methanol induction, where we can now control that feed based off of the dissolved oxygen response of the cells. One thing to note here is that the liquid injection system does have one feed. So what we had to do is we had to have one liquid injection system on the shake flask for the initial glycerol feed in this fed batch phase, and then swap it out with the second liquid injection system, which was loaded with our methanol concentrated solution to be able to optimize that induction. So a little bit of, a one labor step there that we had to really be able to optimize this. And what we found is that a lot of the protein production is actually inhibited by the glycerol in the fed batch phase. So there's really no protein production from about 0.5 mils of concentration to 4 mils of 10% glycerol. And there was a significant drop in pH, especially when we had initially the batch version of the glycerol and then the additional glycerol feeding on top of it. So the way we improved that a little bit is we saw that with higher buffer in the batch phase, we definitely saw better protein production. And then also when we diluted the methanol in buffer as well, we also saw a greater increase in the overall protein yield concentration as well. And so what we decided to do is we decided to get rid of the batch phase completely because of that 0.5 to 4 mil window of no protein being produced. And we decided to just feed glycerol into the system so it would utilize less than that concentration throughout the entirety of the fermentation. And what we also found is it promoted less oxidative stress to the cells. So there was a lot more oxygen recovery and production in the overall yield of biomass and protein when we just decided to cancel out that batch phase and run right into the fed batch phase. And so this is kind of what the new workflow or the optimal workflow looked like. So skip that batch phase, go right into the fed batch phase with that first liquid injection system. And there we had an exponential glycerol feed, biomass being monitored, dissolved oxygen being monitored, as well as that starvation phase where we convert over from glycerol to this methanol induction. And then for the methanol induction, same thing here, that adaptation shot, 1% volume by volume, and then the DO controlled methanol feed with that PID controlled feed. In both phases, of course, still missing that pH maintenance, more improvements to be made. But ultimately, what we found is that after that, we had about 2 more experiments that we ran with this technology. And because we had finally a controller that could respond to the metabolism of the cells, it took about 2 more experiments, starting just at square zero with where we left off with our biomass-based feeding to actually increase this from a 10-fold yield to a 15-fold yield. And so this took around 1 to 2 weeks, took less than 20 liquid injection cartridges. And then we also were able to kind of adjust the design and the workflow of the experimentation from that batch, fed batch, and methanol induction phase to now just a fed batch and methanol induction phase. And the reason this is realistically important is because what we're seeing is that as we add more parameters onto the scale, as we gain more insights, we're actually learning about the different nuances between what keeps cells healthy in the shake flask and what keeps them not so healthy. And I think this is really important when you're evaluating those later phase strain insights from that microtiter scale to be able to relate this to a way to develop insights and say, hey, this feeding profile is optimal. The adaptation time, for example, that I was mentioning earlier, and we'll revisit now, that was really such a critical aspect that we saw, in the shake flasks and in literature, they said that there should be around a 7 to 9 hour adaptation time. In the reactor, every time we ran it, it was 7 hours exactly. And in the shake flask, when we ran it, the adaptation time was also 7 hours exactly. So we're beginning to really uncover the insights at this scale, at the shake flask scale, that can provide translational foundation to designing experiments at the reactor scale. And this is just a first phase of our new technology of what we're really trying to press the boundaries of. And we believe that, as we add more of these parameters on, we're seeing that we got a 15-fold increase from 2 more runs just with 1 parameter addition, which is dissolved oxygen. As we get pH and in the future more parameters, we're just going to see, this bar graph increase to really a trend of understanding how to predict things in reactors at a pre-translational phase. And so that's kind of a big aspect of what we're really trying to do here at SBI is drive home the fact that these insights that we're missing at the shake flask scale are going to be critical for scaling up and scaling down models to understand, a lot more about your processes. And then the last aspect of this is we just really want to create a platform that's easy to use for scientists. I think a huge aspect of this is, we don't want scientists and engineers to have to be spending their time being, glorified biotechnologists. I think scientists and engineers' job is really to be able to draw insights from data and be able to progress or push the envelope forward on a lot of their work, and just focus on, data optimization and where you need to be, whether that be from a research and development perspective or a manufacturing with, critical parameters of interest. So we definitely want to be around an environment where we hand the power back to the scientists to draw these conclusions themselves and really be a well-oiled machine in terms of, progressing their process forward. That is the entirety of the presentation. So happy to answer any questions. And if you're, hoping to connect or learn more about our technology and just understand kind of how we developed a lot of this use case, feel free to connect with us.
Thank you, Jared. So I have one question, and forgive me if you've already touched upon this, but have you considered putting the DOTS technology in really large bioreactors? It seems like it measures pressure, which makes me wonder, can you talk about that a little? How does it measure pressure? Why you're measuring pressure in shake flasks?
Yeah. So I think one of the big things that we've noticed is obviously I'm actually in Colorado right now. So from an atmospheric perspective, if you're in Colorado, the atmospheric pressure is a little bit different, right? So you're going to have variations in dissolved oxygen and possibly performance on your cells with how much oxygen they can uptake. And in regards to the response around putting this in bioreactors, I think that right now we want to master this scale as a stepping stone, because what we've seen is, you have the microtiter, and then a lot of scientists, engineers, a lot of companies that we're working with now have come to us, and they're not getting such good translation from the microtiter right to a glass reactor scale. And that's why we've really focused and honed in on what we're missing at this mid-scale phase. But as for bioreactor parameters, we have definitely had a couple really tenacious individuals ask about, putting these dissolved oxygen pills in reactors. And I think that, in terms of the future, that's something we're looking towards. We just need to master one scale at a time. And we want to become, the people that a lot of individuals look towards to answer questions and question marks about this scale and how we can improve things moving into the reactors. So I think one step at a time, but it's definitely, our eyes on the target for those larger scale endeavors in the future.
Excellent. Yes, it's definitely a very important space as well. And one other, more than this is actually a gift for you, not a question. How would you describe ideal client? What do you want a customer to be doing to be successful with your technology and with your company?
Yeah. So I think for me, what I really, well, there is an ideal use case for us, and I think that we find that in maybe, understanding more about your seed trains or the health of converting cells from this scale to the next, for example, and the health of your cell line from there on out. But I'd say an ideal use case for us is, optimizing media at this scale, or optimizing higher volume, strain selection. So when you have your 1,000 strain selection process and you whittle it down to maybe 12 strains, really being able to do some pre-developmental work on characterizing the process of those strains at this scale is super, super critical. So I'd say that's maybe the ideal use case that we've seen a lot of. It's just, again, those late strain engineering insights and then early stage production insights that we see as a critical aspect. But I will say there's never a shortage of learning from a lot of the companies and individuals we're working with to show that there's so many more applications beyond that. Even something like, an adaptation time use case, or even a use case where you're trying to scale down an operation to convert it from site to site, right? So that's something we've also seen. One company in particular that we've worked with, I can't mention them, but what we've seen is the translation from getting started when you're working at a company where you're employing a CDMO to scale your process. There's so much time spent on making sure that the initial growth phase that you start usually in shake flasks at the CDMO location is matching exactly what you're seeing at your location. And there's a lot of translation lost there. And so one of the suggestions they had is they thought this would be really great technology to say, hey, we'll just ship you these 4 systems. execute the exact same way. And this is the growth curve we can see, because there was a diaxic shift that the CDMO wasn't seeing, that at the company they had seen the whole time because of the online biomass monitoring. So that's just, one use case and where we find, this experiments to be most ideal with our technology.
That's a very good one. And I have a follow-up question on that, but Bruce in the chat has a question. So let me first ask you that. When we eventually transfer to the bioreactor scale, how do we translate the operating conditions, such as shaking speed to agitation speed and airflow, etc.?
Yeah, that's a really great question. And I'm actually going to say that we're working on that right now. We're trying to relate kind of stir speed with how things mix in the shake flask. Obviously, the hydrodynamics of them are completely different, right? So we need to find a way to develop a coefficient to relate the two. Right now, it is, not only a function of stir rate, but we also need to think about, the oxygen levels available in a reactor versus shake flask and take that into account as well. So what we're really looking at is, if you have early trends and indications in the shake flask scale, being able to optimize it to a certain degree, the assumption should most likely be that as you increase that scale with more oxygen, it's going to have better performance. So that's the point we're at right now, but definitely stay tuned, because we are working on that internally, a use case around, relating the two and figuring out, exactly how we can make more sense of that. Excellent.
Thank you. And please keep posting your questions to the chat. So my follow-up question, Jared, to the use case topic we had, and this could be a good segue to the next speaker, is have you looked at microbial cultures that are consortia or communities? Do you have projects in that space? Of course, if you can't share much, you can't, but this seems like a very good way to study them, which it's very difficult to study multiple microorganisms together in shake flasks, well plates, and could be easier to study in shake flasks.
Yeah. So that's, first of all, thanks for the question. I think one of the big features of our technology, especially on the biomass aspect, is that we measure it in a way that you can measure non-uniform morphological organisms in line, like filamentous fungi, for example. And that also paves the path for being able to measure the total number of a consortia within a shake flask culture. But if you have the ability to, for example, tag different organisms with different fluorescence tags, that will absolutely be something that we can apply to kind of projecting how the consortia breaks up when you're mixing different cultures together.
Excellent. Yes, that's what I thought. Again, thank you very much, Jared, but please do stay online in case there's a question.
Yeah, no problem. And I just want to say thank you guys for setting this up. I really appreciate the opportunity to present, and feel free to reach out if you're interested in learning more.
Thank you. Oops, Jared, there is a question for you after all.
Yes, yeah, I see it here. So I'll hop back on. Thanks for a lot of the great questions, Bruce. This is a really great question. So what we've seen in shake flask, for example, is that the growth curve actually looks a little bit different than that of the reactor. As you alluded to, the shear that you're going to see in a reactor breaks the filamentous fungi up a little bit differently. And so we actually see kind of that traditional cell curve from that lag to log to stationary phase in a shake flask. And then at a reactor, I'm sure, with your experience on the filamentous fungi side, we've seen that it's in correlation to the amount of base you add. So it's kind of a linear line. And we've also seen that with higher cell density cultures like filamentous fungi that are non-uniform morphological, there is definitely a similarity to that linear aspect as opposed to that lag to log to stationary phase. It's obviously going to depend on your stir rate, the culture, how much it's actually breaking up the organism itself. But that's just speaking to my experience, what I've seen in one example where we had measurements at a company that started in the shake flask, and then we saw the measurement at the bioreactor scale, and we were kind of realizing that it's actually the impeller breaking up a lot of that filamentous fungi that's leading to the difference in the curve.
Thanks, Jared. Okay, we can now welcome our third speaker of this session, Julia Swavola. Julia is coming to us from Cerillo, and she'll talk to us about co-cultures and how we can do better co-cultures with Cerillo equipment. Go ahead, Julia.
Hi, I'm Julia. I'm Cerillo's head of product, and I'm going to introduce to you Cerillo and our technology platform. So to start off, Cerillo is a small life sciences tools company in Charlottesville, Virginia. We've developed a highly connected platform specifically for microbial cellular analytics in research and development. Cerillo's platform consists of standardized tools that minimize complexity and variability while creating the flexibility necessary for microbial R&D. The compact, easy-to-use plate reader increases throughput, while real-time data visualization makes experimental setup and analysis faster and easier. Cerillo's research tools enable scientists to study microbes phenotypically, generating quantitative, reproducible data in almost any environment. We understand the challenges in microbial R&D and biomanufacturing, so our tools make it easier to study your microbes and scale your product. Our handheld plate reader collects data in any environment continually, and that data can then be accessed remotely. The ease of use and low costs increase throughput and decreases the time to generating meaningful insight. Our standard plate reader measures OD 600 and is capable of kinetic and endpoint measurements. An experiment can be quickly started using the physical buttons or from a computer. And the instrument can be powered through a wall connection, and it can also be powered through an external battery, further increasing the flexibility of its use, particularly in confined environments. As I mentioned, the data is then accessible remotely, and it's usable in flexible growth environments, such as heating up to 50 C, anaerobic conditions, even with microbes that produce corrosive byproducts, and even while shaking, which is really helpful for customers looking at yeast or filamentous microbes. We more recently developed our Duet co-culture system for studying microbes in consortia. The co-culture system enables optical density measurements and other metrics for microbial populations co-cultured in fluidic contact, impacting each other's growth while physically separated by a semi-permeable membrane and then tracked independently. Cerillo's Duet co-culture system is comprised of 2 reservoirs joined by a porous membrane with 0.2 micron diameter pores for isolating microbes, or 50 nanometer diameter pores for isolating phages. The transparent bottom and horizontal alignment of the reservoirs enables continual optical density measurement of each population using Cerillo's plate reader or almost any commercially available plate reader. The 800 to 1,000 microliter reservoir volume allows collection of other along-the-way metrics, such as plating, transcriptomics, or chromatography. As the only commercially available standardized tool for high throughput and independent phenotypic measurements of multiple microbial populations, our co-culture Duet system has opened the door to a wide range of innovative microbial R&D. The combined co-culture and microplate system facilitates the study of microbes in mixed populations grown as closely as possible to their native environment or almost any environment of interest. So now I'll share a few applications that I think will be particularly interesting to this group. These applications are important to biomanufacturing by enabling the study of multiple strains growing together, whether intentionally to support or control the growth of a strain of interest or unintentionally in the form of contamination. The Duet co-culture system enables the impact of one strain on the growth of another to be tracked and quantified. So the first application shows an extremely simple example where the impact of one microbe on the growth of another through the release of a small molecule was observed. Here, 2 bacterioid species were observed in co-culture, one of which produces indoles and the other does not. The growth kinetics were monitored continually with OD 600. Indoles, represented as the pink hexagons, diffuse across the 0.2 micron filter, while the bacteria were isolated to either side. Unfortunately, I can't show data for this and the next few applications, as it's proprietary. I will show data from a co-culture experiment later in this presentation. So another application is the study of lytic bacteria, which attack, consume, and metabolize other microbes. The goal of this study is to identify the mechanism of killing of the lytic microbes, which could be used to control the population growth of another population. So this application looks at two symbiotic strains of bacteroids which require the presence of each other in order to thrive. And these strains are grown and studied in the duet co-culture system, where one bacteroid can metabolize a high molecular weight polysaccharide, and the other one can only digest byproducts of the other's digestion. During this experiment, both the high molecular weight polysaccharides and its byproducts diffuse across a semi-permeable membrane, and growth kinetics were measured with OD600. This application shows a more dynamic growth environment with complex interactions that could impact fermentation for a target microbe. This application shows the determination of the minimal inhibitory concentration for a small molecule inhibitor against a contaminating microbe while preserving growth of the target microbe. This could be another effective strategy against contaminating microbes. So as promised, some real customer data. The final application I'll show is from a researcher who used a duet co-culture system to study microbes in consortia in an environment as close as possible to how they naturally flourish. The data on the left compares two growth and analysis methods for a 3-microbe consortia. The top graph shows data continually collected using the duet co-culture system to physically isolate one microbial population from the other two populations in consortia. In this case, measurements were collected with our Alto plate reader. The bottom shows the traditional method of growing the 3-population microbial consortia in a shake flask and then periodically plating and counting CFUs. As you can see, the data generated with our system is much cleaner and more quantitative. So I went through just a few applications. This table shows other really creative applications where it's been used, including struvite kidney stones, arsenic tolerance, phage bacteria interactions, and even treating fungal infections currently threatening frog and salamander populations. So I'm actually gonna, I think I'm running out of time, so I'm gonna skip this slide, but we've developed
I think you have time, sorry to interrupt, but you have another 7 minutes.
Oh, wow, I'm looking at the wrong clock. Sorry, I've been speaking really quickly. Okay, perfect, thank you. All right, so as I've shown, our platform facilitates the standardization while minimizing complexity and variability. The system also enables the flexibility necessary for microbial R&D and quantitative data generation necessary for generating insights and scaling to industrial systems. So we started with our plate reader, which increases throughput, provides real-time data visualization, and makes experimental setup and analysis faster and easier in any growth environment. And then our duet co-culture system allows researchers and technicians to study their target strains in more optimal and more realistic growth environments. Our research platform enables the studies of microbes phenotypically and quantitatively and reproducibly in almost any growth environment, because R&D and biomanufacturing is already difficult. So Cerillo is continually developing tools to help study and scale your microbes. Our technology is already used in many academic, government, and industry labs all over the world, and we're continually looking for new applications, collaborators, and partnerships. So I invite you to reach out, join our community, try our platform for your application, or let us know how we can integrate your research and product development in the future as we grow.
Thank you, Julia. And if you feel like you rushed through 1 or 2 slides, we can definitely go back and review them if you.
I'm okay. Sorry that was
No
a little bit
issues.
rushed in the middle.
And,
I'm happy to
and
take
maybe some of the questions will lead you there. I do have questions. One is a question that we talked about before this presentation around studying contamination in large-scale cultures. So in industrial biotech, we can go up to 100,000 liter scale. That scale, if we are using granular feedstocks, it's really difficult to keep everything sterile and for long periods of time. So if we wanted to study the dynamics between the contaminant and the microorganism, and there's some research out there already, Felipe Lino's work from TU Denmark being some of that. If we were to use Cerillo's equipment for that, how would we control the growth rate of the organisms so we can simulate the conditions at really large scale? For example, we wouldn't expect the contamination to outgrow the culture for a long time. So we would have a micro contamination. How would we simulate that in Cerillo's equipment?
Interesting. So we haven't seen anybody actually use that application. That's really, I think that you could do it. You could approach it in a couple of different ways. And that was actually, so I'll go back to some of these examples, and that's why I chose them. So I think I would approach it from one of two directions. One would be looking at a strategy to control the growth of the contaminating microbe, though I think that your question is more along the lines of how do you make sure that you're mimicking the growth rates accurately? Okay. So because the volume is higher than, say, a 96 well plate, and you have more nutrient and gas availability than a 96 well plate, I think it presents a good intermediate for scaling and a really good high throughput mechanism for studying the relative growth. I don't know that you would be able to, with this system, exactly mimic, but within that, I would say that if you were to, so we have data showing as one microbe which lags behind, so a microbe with slower growth grows and reaches its carrying capacity, it does impact the growth of the other. And so we can generate data showing how one impacts another strain, or you could even go in and over time replace media and see how let them grow for longer and see over a longer period of time how they impact each other. And one thing I will also add is specifically for studying slower microbial growth or microbes starting at a much smaller, lower concentration, that is one of the areas that scientists have found this system particularly useful. Sorry, does that answer your question?
Yes, it does. And I have a follow-up on that question around growth rates. You've looked at growth rates of two different organisms in the system. Have you considered looking at taking an older culture, as in maybe it's hitting the stationary phase, and comparing it next to a early exponential phase culture? Reason, and this may sound very facetious, but you know how there's some very, very empirical evidence that young people's blood contains some youthful ingredients that old people's don't. I'm wondering if that is true in microbial settings too. Just wondering if you thought of comparing two different cultures of the same strain.
So we don't, other than having some application notes, and then I support scientists looking at really creative studies, I would say that definitely could be studied. It would be really interesting to study that. I know from other experience that there are definitely things in that media for older microbes at stationary phase, because the refractive index actually changes, meaning there is something different in the media. I think that'd be a really interesting application to look at if somebody wanted to do that.
Let's do it. Let's do it.
All right.
Thank you. Thank you very much, Julia.
Thank you.
Thank you very much. Okay, so now we move on to our next speaker, Jeff Thornton. Jeff is a very highly experienced person you should know anyway, but in his current role in OmniBRx, he's going to talk about the bioreactors from the company.
Yeah, hi Deepti, how are you? Nice to see you again. Can you see my screen?
Nice to see you, Jeff.
Yeah, nice to see you. It's really nice actually to be part of this. Also, thank you very much for having us, inviting us. What's really neat about this is to see former colleagues on this, like Julia. I know Julia from a prior life as well, and they're great technology. And a lot of the folks I've worked with at ABPDU, you guys are fabulous, and you have a fabulous facility. So thank you again for having us and having this for everybody. I think all the vendors probably have that same sentiment. So thank you again, Deepti.
Absolutely. You're all teaching us.
Okay,
Thank
great.
you.
So, well, what else? That's a great segue. So what I hope to do today is give you a little introduction into OmniBRx and our bioreactors. And I'm the director of sales here at OmniBRx in the US. I'd be really shocked and surprised if you have heard of OmniBRx. We have a really huge presence in Asia. But in the US, our footprint's only been established for the last couple of years. What I'm going to do is give you guys a quick overview of OmniBRx, who we are, and the products that we sell, which are primarily bioreactors. So I'll skip to the next slide. Who we are, we're primarily a bioprocess technology company that's engaged in the design, development, and manufacture of single-use bioreactors. We supply some of the world's biggest vaccine developers and the pharmaceutical industry to develop vaccines and biologics and drugs. And our portfolio, I'm going to be just speaking about the bioreactors and our consumable line, our SUBs or single-use bioreactors. But our portfolio actually encompasses or has a lot of services as well. And so we span nearly all steps of that bioprocessing, from R&D and scale up to manufacturing. All that manufacturing, and we'll talk about that in subsequent slides, would happen in our manufacturing facility, which is located, oops. Now my screen is frozen. There we go. Did it switch to the next slide, you guys?
Yes.
Okay. So I'm based here in the US. If you can tell by my accent, I'm on the West Coast of the US. But our sales office is based in North Carolina and RTP. Our R&D and our manufacturing plant are based in India. They're based in the state of Gujarat in India. So that's where like our CGMP facility is. Any of the vaccine development and optimization that goes on would happen there. But I'm based in the US. We've sold close to 100 systems to date. And most of those sales have come through a distribution network that we have established in Asia, primarily in India as well, but throughout Asia, we have a pretty extensive distribution network. About 2 years ago, we branched out into the US, and we're getting ready to branch out into Europe as well going forward. This is our team. You can see we have combined lots of experience, I think over 80 collective years in the bioprocessing industry, from Beckman Coulter and M2P labs, where some of you guys may know me. I used to come into ABPDU with our BioLector. That's when I worked for M2P that got acquired by Beckman Coulter. I met my colleague Jagadish there, and he brought me on to Omni about 6 months ago in June. But you can see a lot of our team has experience with Cytiva, Sartorius, Beckman Coulter, and so on. We do a lot of things. I'm only going to be talking about equipment and consumables today, but you can see we offer a lot of process development and optimization services in our facility in India, our CGMP facility that's there. But again, I'm just going to be focusing on our bioreactors. And what's cool is this seminar and this 2 days, we've all been kind of talking about similar things, and a lot of the common denominator is bioreactors. Any of the cells you're growing, whether it's microbial or maybe algae or even mammalian, bioreactors seem to be present everywhere. And a lot of the cool science that's being done these days is being done with bioreactors. And I'm here today to tell you about some of our bioreactors. And we offer about 6 different bioreactors. I'm really just going to talk about 2 today, the CELBRX and MiniBRx. And when we were sending our slides out, Deepti had actually given me some great feedback. Hey, our processing here and what we do, and the CELBRX system is really for more of that biopharmaceutical industry. And I would 100% agree with you, Deepti. And I did leave it in, and I want you to understand why. It's really great for cultured meat platforms. It's a great cultured meat platform. And I know in the Bay Area, there's a lot of startups and companies that are doing that. And they may be working with suspension cell cultures now. But ultimately, I think they're going to move to the adherent kind of cell culture and that type of platform that can accommodate that. And so for that, I left it in DP, just FYI. But I did put in some slides about our MiniBRx for fermentation as well. So thank you for that feedback. But here's what we're going to do. We're going to talk a little bit about CELBRX and then a little bit about MiniBRx. The CELBRX, again, is for adherent cell lines. It's really where our competitive advantage lies. Again, these are single-use bioreactors. It's really been designed for vaccine and viral type of work. But over the last couple of years, a lot of meat companies have come to our attention and said, hey, your reactor looks great. And I'm not going to speak about all the little tubings and connector ports and things, because we all know how those work, right? What I'm going to speak about is just up in the upper right-hand corner is the CELBRX SUB, or single-use bioreactor. And what you can see on the inside of that chamber, and we're going to see a blown-up view of it, is this SUB actually has the largest surface area out there for bioreactors at the volumes that we provide. And how we've achieved that is we've added increased surface area to the interior of that bioreactor. And we've set up these discs or these scaffolds that are attached to these rods. And you can see here it just offers the largest surface area of any reactor vessel out there. What I want to show is this. Hopefully you're seeing the screen now that shows kind of the DBR technology, dynamic bed reactor technology. What it is a series of circular discs that have been stationed in the interior of that reactor on these shafts. And all those shafts rotate independently. And so around those discs and around those shafts, you also have like, looks like a jet plane blade. That's going to rotate as well. And in the next slide, you'll see a video. I hope it plays. Let me see if I can get it to play. You can see how it's rotating. And so that outer fan blade is forcing all the liquid to the interior of that shaft and those scaffolds. And you can see here just with another perspective of it spinning around. And it really ensures really nice homogeneity throughout the mixture. Just like any bioreactor, we're going to be able to measure all those parameters that you want to measure. Oops. So sorry again for this non-presentation mode, you guys. So just to summarize the CELBRX platform, again, full scale of this, all the way down to 250 mLs. I know it shows 350 ml there, that's the reservoir, but basically from 250 ml all the way up to 200 liters, we have that dynamic bed reactor technology available. So I know you guys maybe aren't doing, say, adherent cell lines yet. If any of your Bay Area meat customers come to you, tell them you know a way how to do it now, right? Or if any of your friends or colleagues are doing, say, studies with adherent cell lines, please let me know. One thing that was really cool that we did with the CellBRx system, real quick to finish up on this, is we linked a 1 liter, a 5 liter, a 10 liter, and a 50 liter together for a viral vector manufacturer. And they wanted a closed loop system where they started at the 1 liter, generated enough cells to inoculate the 5 liter, to generate enough cells to inoculate the subsequent bioreactor at 10 liter, and so on to 50 liter, which they used for production. So it was kind of a neat thing we accomplished this year with that. What we'll talk about next is the OmniBRx. Again, this is going to be probably what is more relevant to the folks here on this call and doing the fermentations. These are single-use mini bioreactors for suspension cell cultures. Your high throughput screening, maybe your process development and optimization studies, any fermentation studies. We offer both integrated perfusion and fed batch reactors. We'll get into that. They're set up similarly to other 250 mil based systems that are out there on the market. This one, they're set up into quad reactors. So basically we can put 4 reactors on each one of these quads that's shown. You could link all 4 together and have 16 parallel reactors running at one time. And each one of those reactors can be controlled independently. So any of the parameters that you can measure or change, you can change independently for each one of those reactors. It doesn't affect, say, all 4. It's each one individually. And again, it's all controlled by this SCADA-based advanced process system. And these reactors come in both a perfusion and fed batch setup. Typically customers run 250 mLs, but you could run at different volumes if you wanted to. I know time's up. We're going to rip through Deepti real quick.
Sure, thank you.
Real quick on these, it offers some unique type of sparging. It's got some tubing wrapped around the interior of those wells. It actually is kind of nice. So it's like a ring sparging, but pH 5.5 to 8.5. These are all optical sensors. We have sensors for biomass, glucose, lactate. We have custom sensors. We have a off-gas analyzer if you wanted that. The software is 21 CFR Part 11 compliant. We did a side-by-side with your favorite 250 mil system, and you can see that ours are in red, theirs are in blue, and we lined up spot on. This was a CHO cell experiment, but in terms of cell growth, viability, and expression, we were on par. That wraps it up. Next year, we're launching a micro mini, which is going to be focused specifically on fermentations. We're developing a system specific for large-scale meat culture. That's ongoing. One of the unique things about that are the scaffolds that you need to use. You need those edible scaffolds, and that's why that CellBRx system with those scaffolds are really interesting for them. You can see we work with a lot of leading vaccine producer of the world, Serum Institute of India. That's something I learned when I came on board 6 months ago. That's it, you guys. If you want to do a demo, let me know. Here's my contact info. Sorry, Deepti, for the technical issues. And
No problem, no problem. Thank you very much, Jeff. In the interest of time, I'd encourage you to direct your questions to Jeff to the chat so he can respond to you. And Jeff, if you want to leave your email ID in the chat because we couldn't put up your contact slide for too long, that would be good for the attendees.
Thank you.
And now we move to our next speaker, Stephen Hubbard, who's going to talk about Eppendorf and not just the reactors, but their digital strategy and many more things. Take over from us, Stephen.
Okay, great. So first of all, hello, everyone. It's really a pleasure to be with you all. The bioprocess community is populated by some really excellent folks, and I notice a lot of friends on the call and many people that I look forward to crossing paths with in the future. thank you to Deepti and ABPDU for organizing this and also for helping me get my start in this field a long time ago when I worked at the ABPDU, a very impactful time for me. So I'm going to be talking about Eppendorf bioreactors and our tools, our software tools helping improve bioprocess generally. All right, how do I advance? There we go. A quick history of Eppendorf. The Eppendorf organization was founded in 1945 in Germany, and the New Brunswick Scientific was founded in 1946 in New Jersey. Was not part of Eppendorf originally. DAB.bio, also a separate entity, was founded in 1991. And then Eppendorf acquired New Brunswick and all of the New Brunswick reactors, acquired DAB.bio in 2012. And recently, the portion of Eppendorf that focused on bioreactors kind of became a little bit more vertical, a little separate from the rest of Eppendorf. I'm happy to connect you with the folks who will support your centrifuges and pipettes, but that's not me. So Eppendorf really tries to be a one-stop shop for everything you'll need for your bioreactor processes. We've got scalable systems. I'll briefly mention the single-use solutions. We'll talk a lot about the software, and at the end, I'll make note of some of our services and supports. Also, a couple of my colleagues from the service team are on this call. If there are questions specific to them, they could answer later. This is what our portfolio looks like. We've got reactors down to 250 mils. That's the DOS box unit. And maybe you've seen the DOS GIP unit, which is a little bigger. JBay has a few of these. Then you see the Cyverio and the BioFlow 320 benchtop bioreactors. Those are right in the market for benchtop bioprocess development teams. Then you see the BioFlow 720. That's a single-use reactor, and that is a BioFlow 610 on the right, an SIP reactor. We have SIP reactors up to over 2,000 liters. We also, as I mentioned, have many single-use reactors, both fermentation-specific and cell culture-specific, many sparger and impeller and sensor configurations. There's really a lot of tools here that improve ease of use and turnaround time. Some interesting stuff there. I'm really excited that we've recently released a Eppendorf-specific auto sampler. So when I was at ABPDU taking samples at 2 in the morning so that we can get that time point, we could have had the bioprocess auto sampler. And this integrates really nicely into our SCADA for our reactors. Now, with all of these great tools and all of the many tools that the other presenters have been talking about, I think we can recognize that bioprocess data has gotten really complex, especially over the last 10 years. So many new sensors, so many types of reactors and controllers and peripherals. And Eppendorf has been focused specifically on this problem. We want scientists to be doing the science, not the difficult data engineering and manipulation that has taken so much time for people in our field for a long time. So I want to highlight that DOSware is the SCADA, the supervisory control and data acquisition platform for our reactors. And this really allows a high degree of complex programming and monitoring and control and communication with external and controllers and data historians. The communication protocols are OPC UA, which we find to be the standard, and we think that's going to be the standard going forward. So I'll just point to a quick case study that we did with the integration of a third-party Raman analyzer. This is a collaboration with Merck, and you see the applications note here if you wanted to read more of the specifics. We have 3 applications labs full of bioprocess scientists and engineers who work with our reactors and our software and sometimes other software and equipment to prove out all the capabilities that we know our customers will need. In this experiment, the Raman sensor was used to create a control loop to keep the concentration of glucose at 5 grams per liter and optimize viable cell density throughout this process. Okay, so something that's going to be new to many people. You've probably seen lots of the stuff that I've already presented, but some new things. BioInsight Cloud is one of Eppendorf's big steps towards making data management and communication about data, monitoring and analysis much more straightforward. So the way that BioInsight Cloud works is that a lab will have DOSware, or a company can have multiple labs with multiple DOSware computers at the same site or across the world, and all of the data coming off of those bioreactors is stored both locally and, when enabled, in the cloud. This is a Microsoft Azure-based cloud, and the security protocols actually are a very important thing, and there's a specific white paper about cloud data security. I would love to forward that to anyone who's specifically interested there. But many of our customers use this as a, hey, I'm just going to check how the reactors are doing on my phone or iPad or laptop from home. Many people just have this screen up at their desks so they don't have to go into the lab. They can monitor everything. And also you can compare every fermentation run that has ever happened at your site against any other. There are some great features in here, like you can select a quote golden batch and compare the current runs or other runs against that. And then I want to talk about another software as well, and that is called H.E.L. And I'll just say that yes, these are multiple softwares that are new. I like to think of what's happening as our field is getting a more robust tech stack. My friends in robotics, they use this word tech stack. It's the collection of hardware and software tools that are used in advanced workflows. And I'm really excited about the addition of the H.E.L. lab to the tech stack. So data is collected in DOSware, captured in the BioInsight Cloud for monitoring and analysis, and then customers who have the H.E.L. lab software can easily pull their bioreactor data into this H.E.L. platform, which really is a hybrid artificial intelligence model that helps generate and highlight insights about what is going on inside of an organization's bioprocesses. There's a lot of customizability. I think the real thing to highlight here is this model that is generated by the customer is owned totally by the customer. We don't have access to it. H.E.L. does not have access to it. The H.E.L. organization does not have access to it. It lives with you. I'll point to a quick case study. This actually was published in Biotechnology Journal a collaboration between this Data.how lab organization and BMS, and they wanted to use these hybrid models that just look at the data, but also use mechanistic understandings of processes to predict critical quality attributes. So with the black box model, that is not a hybrid model, there is 60% of the ability to explain variance in those critical quality attributes. With hybrid models, it goes up to 80%. There's more here. We can get into that maybe offline. One thing that I think is really important to all of us running laboratories is how many experiments are required in process development to really figure out what is going to happen. And with black box models of the data, you really need upwards of 30 experiments to get a good sense of the quality attributes. And this is showing that with many fewer experiments, you can make really good models that will predict quality attributes. So Data.how, relatively new, and we are excited to explore all of the uses with our customers. I would love for folks who are interested in how Eppendorf is helping our customers use the power of artificial intelligence to understand their data, please reach out to us. Lastly, I want to talk about the fact that Eppendorf has one of the most robust service and support teams I have seen in our industry. In America, we have over 20 field service engineers and application specialists. There's remote support in a separate technical product support team. And we have international teams that mirror this level of support for our customers. One of the benefits of the fact that we've been around for a long time and that we serve so many customers in so many fields is that we've built up a robust team to make sure that you get the equipment that you need, but also the expertise in setting up, in automating, in scripting, in troubleshooting your processes. I also want to point to the fact that we have these service agreements, and actually Jeff is on the call, and if there are specific questions about them, he can take some of those questions. But advanced care and premium care, these are plans that exist throughout the year, include a yearly preventative service, a visit for the equipment. Yeah, we really want to make sure that you get taken care of for the life of your equipment. Okay, with that, I'll point to these links for our products and also our list of application notes and areas of support. I think that if you click around the Eppendorf Bioprocess website, you'll find that there's a lot of information. We really go out of our way to demonstrate that we are supporting everyone in this community as best as possible. Okay, with that, I'd love any questions from the audience.
Thank you, Stephen.
You're
yes,
very welcome.
there is one question.
Yes.
Does DASware work with all your bioreactors or just the DASKIP DASBox?
Yes. So in the past, it was just DASKIP DASBox. It now works with many, many more of our reactors. The BioFlow 120 and 320 reactors. Cyverio is built for DASware. And in the future, there are plans to use it for even our larger reactors.
Excellent. And a question I had, and I fully appreciated your comment on sampling, overnight sampling especially. Can your autosampler work with filamentous fungi or some kind of high cell density fermentations? And How do you know you're taking a representative sample, especially when if you're working with filamentous fungus or some other?
Yeah, so the autosampler has been released in stages. First for mammalian cell culture, recently the microbial version has been released, and there has been rigorous testing. I don't know specifically whether there has been testing with filamentous fungi, but I do know that with high density fermentations, there's been a lot of work put in. I'd love to follow up and connect you to the people who have actually done that work in our applications lab. The last thing I'll say about that is if there are people who want to investigate our autosampler more, we have them set up in our applications labs, and potential customers can visit those labs with coordination to see them in action.
That's excellent. Yeah. Thank you very much, Stephen. And in the interest of time, if anyone else has questions for Stephen, please feel free to follow up with him or put them in chat if he's going to be around for a minute or two, but feel free to follow up with him for sure. With that, we come to an end to our second expo, virtual expo that ABPDU has conducted. Thank you very much for all of the audience who've stuck around with us since yesterday morning. Thank you to the speakers for doing a wonderful job. We had 38 speakers. I was pretty sure that we'd have at least one or two missing in the last moment or someone's internet would fail, but surprisingly, everything worked out very, very well. So thank you to the speakers. Thanks to Ning and James and Eric for moderating the event. But I really, really want to thank two people who've been in the background here, Emily Nelson and Leah Sloan. They've done a tremendous amount of work to bring this all together. Thank you all very, very much for this very successful, wonderful event. And looking forward to being in touch with this community. Please do write to us at abpdu@lbl.gov if you have any questions, comments about this expo or anything else. Thank you all again.